Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So, my dear students, quickly just let me know if all of you can hear me, if I'm perfectly audible and visible to everyone. Quickly let me know in the chats with the thumbs ups. With the thumbs ups. Quickly let me know in the chats. Quickly, people. Good evening, and welcome back. Good evening and welcome back, guys. Good evening and welcome back. Welcome back. Perfect. So, my dear students, do you remember till what topic did we discuss in the last session? Well, first of all, let me tell you, till now we are done with 2 sessions of thermodynamics, and today it's going to be the last session of the chapter thermodynamics. We are going to discuss something really very important. Some topics from which questions are frequently asked in your NEET as well as JEE examination. All those topics I'll be covering in the today's session, right? And the session duration will be maximum for 3 hours. So we are not going to take any break in between. So 3 hours straight and let's finish the chapter off. And my dear students, on Saturday at 5 p.m., we are going to have the one-shot session of the chapter chemical equilibrium, right? Shravan, thermochemistry will be dealt. That's a separate chapter basically, thermochemistry. Right now I'm talking about thermodynamics, right? Thermochemistry will be done after this. Perfect. So today we'll be completing thermodynamics part. On Saturday we shall be completing chemical equilibrium in one shot, right? And in the upcoming week we shall be completing the thermochemistry part as well. Okay? Yes, absolutely. They are more than sufficient. Perfect. So if you remember in the last session, we discussed till the free expansion. Free expansion was the last topic which we discussed in the last session, right? So right now, we are going to start with the topic that is cyclic process. One of the important topics of the chapter, right? And my dear students, this particular topic is in your physics as well. And a lot of questions are asked from this topic in physics as well. So I'll try to make sure that after discussing the cyclic process, you should be able to solve all the questions in physics thermodynamics as well from the same topic. Yeah? Perfect. So are you guys ready for it? Are you guys ready for it? Quickly, let me know in the chats. Are you guys ready for it? Give me some thumbs up. Let me see the Josh of the session first. Quickly, people, in the chats, everyone in the chats, are you ready for the session? Are you all ready for the session? Say yes or no in the chats quickly. Perfect, guys. Perfect. So let's get going then. So before discussing the topic cyclic process, there are a few basic things which I would want to share with you. And what are those basic things? Let's have a look. My dear students, over here, I'm going to make a pressure volume curve. I'm going to make a pressure volume curve over here. Along y-axis, I'm plotting pressure of the gas. Along x-axis, I'm plotting volume of the gas. For example, I'm selecting 2 points over here. This is point A, and right here, this is point B. Okay, I'm selecting 2 points, point A, point B. For example, when the gas was at point A, when the gas in the container was at point A, let's assume volume of the gas was V1. And when the gas reached the point B, volume of the gas, for example, is V2, right? And over here, what exactly I'm going to do? I'm going to draw a straight line. And I'm showing the arrow towards the right, for example. Perfect. Can you let me know what should I be calling this particular curve as, this straight line? My dear students, do you see at every point on this line, pressure of the gas is remaining constant. Pressure of the gas is not changing, right? At every point on this line over here, at every point on this graph, pressure of the gas is remaining the same. So first of all, should I be calling this particular curve as isobar? Absolutely, I'll be calling this particular curve as isobar. So this AB, it represents isobaric process. It is simply telling you that the gas is undergoing isobaric process, right? It is simply telling you you are changing the state of the gas, but you are making sure on changing the state of the gas, you are not changing the pressure of the gas. Yeah? So point number one. Point number two, my dear students. Have a look at exactly what I'm going to say. If I draw one more straight line like this, and for example, I'm showing arrow downwards or for example, arrow upwards, whatever, right? Leave the arrow aside. I'm drawing one straight line over here. Can you let me know this straight line over here, this graph, which thermodynamic process it represents? Can I say it represents basically your isocoric process? It represents your isocoric process. Perfect. Take any point on this graph. At every point on this graph, volume of the gas is remaining constant. Volume of the gas is not changing. So this particular line over here, it is simply telling you that the gas is undergoing isocoric process. What does that mean? That means you are changing the state of the gas, but you are making sure the volume of the gas does not change, right? You are changing the state of the gas, but you are making sure that the volume of the gas does not change. Perfect. So this line over here, it represents isocoric process. At the same time, my dear students, if I draw two curves like this, if I draw one hyperbola and for example, one more hyperbola, I'm showing arrow towards right. I have drawn two hyperbolas over here, right? If you remember, I had told you in the last session, place your thumb at the common point, curl your fingers in the clockwise direction. That curve which touches your fingers first, that has to be the isothermal. Curve, and the other one automatically it becomes the adiabatic curve. This is something which I told you in the last session. Perfect. So my dear students, the first line which I've drawn over here, in which pressure of the gas is remaining constant, you are simply saying the gas is undergoing isobaric process. Similarly, this green colored line, the gas is undergoing isocoric process. The gas is undergoing isothermal process. The gas is undergoing adiabatic. I hope this is something which every one of you must be knowing now. Yeah? Perfect, clear? Now, after this, we are going to start with something called a cyclic process. Let's get to know exactly what this cyclic process exactly is all about. My dear students, I'm going to start exactly from the basics so that you can understand it properly, okay? First of all, as far as the definition of cyclic process is concerned, it is defined as that thermodynamic process in which system returns to its initial state. That thermodynamic process in which the system returns to its initial state after going through a lot of steps. Okay, after going through a lot of steps. Now, what does that mean? For example, again, I'm going to plot a PV curve over here. This axis represents the pressure axis. This axis over here represents, for example, the volume axis. Now, my dear students, for example, I'm starting from point A. Let's assume that, first of all, I'm going from point A to point B, right? Then, for example, I'm going from point B to point C, right? And from C, I'm again coming back to A. So what has happened exactly? Can I say the system is returning to its initial state after going through a lot of steps? The first step which the gas is following, that is AB step. The second step is BC step. The third step is CA step, right? So I would categorically say the gas, which is my system, the system is returning to its initial state after going through a lot of steps, right? whenever you see this kind of the process, this kind of the thermodynamic process in which system returns to its initial state after going through a lot of steps, you will say that your gas is undergoing, your system is undergoing a cyclic process, right? Can I say in case of the cyclic process, the initial state and the final state of the system is same, right? Initial state and final state of the system is same. See, we started from A and finally we reached to A as well, right? So whatever was my initial state, same is going to be my final state. So I would categorically say, in case of cyclic process, the initial state and final state of the system is same, right? At the same time, if you remember, I have told you categorically, change in the value of a state function. Change in the value of a state function for a cyclic process, that's always 0. What is the state function? State function depends only on initial and final state of the system. If the initial state and final state of the system is same, I must say change in the value of state function will be absolutely 0, because the initial value of state function and final value of state function, that will be obviously same. Therefore, change in the value of state function for a cyclic process is 0. What does that mean? That means delta U net, or I'll say change in internal energy for the cyclic process, that has to be equal to 0. Enthalpy change during the cyclic process, delta H cyclic, that has to be 0, right? For example, delta G for the cyclic process, this will be 0. Similarly, delta S for the cyclic process, this absolutely again will be 0. What are these U, H, G and S? U stands for internal energy, H stands for enthalpy, G stands for Gibbs free energy, S stands for entropy. All are state functions basically. And we already know change in the value of a state function for a cyclic process, that's always taken to be 0. Perfect. My dear students, if these points are clear to you, let's try to analyze them a bit more in detail. Let's try to understand few important things. Have a look what I'm going to say. Since I told you delta U net internal energy change during the cyclic process, that's always 0. Absolutely. Perfect. Now delta U net is simply going to be equal, as per the first law of thermodynamics. Delta U is equal to Q plus W. So I would say delta U is equal to Q net plus W net. So Q net plus W net, it has to be 0 in case of the cyclic process. Or you can say Q net has to be equal to minus times W net for a cyclic process. This particular statement is valid for a cyclic process. Q net is always equal to minus times W net for a cyclic process. Perfect. I simply use the first law of thermodynamics. We know delta U for the cyclic process, that's 0. Delta U is nothing, that's Q plus W. If delta U net for the cyclic process 0, therefore Q net plus W net has to be 0, or you can say Q net is equal to minus times the W net, right? This is one statement. One more statement. Few minutes back, if you remember, we have drawn a cyclic process like this. This was your pressure, this was your volume. You started from point A. From point A, you reached to point B. From point B, you reached to point C. From point C, you again reached to point A. So this was my cyclic process. Can I say this particular cyclic process actually contains 3 steps? First, the gas is following the process AB. Then the gas is following the process BC. Then the gas is following the process CA. So my dear students, as I told you, delta U net internal energy during the cyclic process, that has to be 0. What is this net internal energy change during the process? It simply is change in internal energy for the gas during the process AB plus change in the internal energy of the gas during the process BC plus change in the internal energy of the gas during the process CA. This whole term has to be 0. Point number 1, right? Similarly, point number 2. If I ask you what is Q net basically? What is Q net? Q net is basically net heat absorbed or released by the gas during the cyclic process, right? What is delta U? Delta U is the net change in internal energy, total change in internal energy of the gas during the cyclic process. That has to be 0. If I ask you Q net is total heat absorbed or released by the gas during the cyclic process. That also has to be equal to QAB plus QBC plus QCA. What is Q net? Total heat absorbed or released by the gas during the cyclic process. That has to be equal to heat absorbed or released by the gas during the process AB plus heat absorbed or released by the gas during the process BC plus heat absorbed or released by the gas during the process CA. Perfect. Similarly, if I ask you, what about W net? What about W net? Net work done during the cyclic process. Net work done during the cyclic process. It is also going to be equal to work done during the process AB plus work done during the process BC plus work done during the process CA. I hope all these terms are absolutely clear to everyone. Yeah. Now, my dear students, there are a few more things which I would want to share with you. And what are those things? Let's have a look. Let's have a look. First of all, let me tell you, area enclosed by the loop. Area enclosed by the loop. What is meant by this area enclosed by the loop? This is basically the area which is enclosed by this particular loop. Whenever you'll be calculating the area enclosed by the loop, area enclosed by the loop always gives us the magnitude of work done during the overall process. Whenever you need to calculate the magnitude of work during a cyclic process, what you have to just calculate? You just have to calculate the area which is enclosed by the loop. Whatever area is enclosed by the loop, that's something which is going to give you the magnitude of work done during the cyclic process, right? And my dear students, two more things which I would want you guys to remember. Whenever you see the clockwise cycle, whenever you see a clockwise cycle, whenever you see a clockwise cycle, have a look over here. Look at the arrows. First arrow is in this direction, then it goes downward, then it goes in this direction. So it's a clockwise cycle basically. It's a clockwise cycle. During clockwise cycle, the value of W net, it comes out to be negative. During clockwise cycle, the value of W net, it comes out to be negative. You'll get the idea in some time. And similarly, during the anti-clockwise cycle, during the anti-clockwise cycle, the value of W net will come out to be positive. Will come out to be positive. So my dear students, whatever points I told you till now related to cyclic processes, all these points will be using in the questions, and I'm 100% sure if you remember all these points, for the cyclic process, you can easily solve all the questions based on the concept, right? So let's have a look exactly what kind of questions are asked and how do we deal with the questions. Yeah. So are you guys ready for the questions based on the cyclic process? Quickly, let me know in the chats. Quickly. This is the first and the basic question. The first and the basic question. Have a look, people. First of all, you are given with the pressure volume graph. This is the pressure volume graph, right? We are starting from point A. When the gas is at point A, its pressure is P1, its volume is V1. Then the gas reached point B, where its pressure is 6 times P1, its volume still is V1, right? Similarly, then the gas undergoes the process BC. Then the gas undergoes the process CA. So can I say the gas is returning to its initial state after going through a lot of steps? Absolutely. So should I be calling this particular process as a cyclic process? Absolutely. So I must say the gas which is there in the consideration, the gas is undergoing the cyclic process. First, the gas is undergoing the process AB, followed by BC, followed by CA, right? One thing. Second thing, my dear students, is the cycle clockwise or anti-clockwise? The cycle is anti-clockwise. Sorry, the cycle is clockwise. If the cycle is clockwise, the sign of W net has to come as negative. Sign of W net, net work done during the cyclic process, it has to be negative, right? Now, if I ask you, what about the magnitude of work done? What about the magnitude of work done during the cyclic process? As I told you, magnitude of work during the cyclic process is equal to area enclosed by the loop. How much area is enclosed by this particular loop? This is the area basically which is enclosed by the loop. It is enclosed by the loop. Do you see it is basically a right angle triangle? Can't we calculate area of the right angle triangle? Absolutely. So net work done is basically equal to area under the loop. Sorry, area enclosed by the loop. Area enclosed by the loop, and the loop is ABCA. Area enclosed by the loop ABCA, right? So I would say magnitude of net work done during the process is equal to half of base into height. What is base? It's going to be equal, see, from here to here it's V1. From here to here it's V1. Then from here to here, it is, see, it is V1 from here to here. Then from here to here, it's 3V1. So from here to here, it's going to be 2 times V1, right? Simple. Perfect. So half of base is going to be 2 times V1. And what about this hypotenuse? What about this hypotenuse? So from here to here, it's P1. And from here to here, it's 6P1. So hypotenuse has to be 5 times P1. Perfect. So half of base into height. Base is 2 times V1. Hypotenuse is 5 times P1. So 2 got cancelled. The values coming out to be 5 times P1 V1. So this is basically the magnitude of work done during the cyclic process. But am I supposed to calculate magnitude of work, or I'm supposed to calculate the net work? I'm supposed to calculate the net work done during the process. I would say net work done during the process will be equal to, sign has to be negative. Magnitude is 5 times P1 V1, right? So this is the net work during the cyclic process. Yeah? Is this clear to everyone, people? Quickly in the chats. Is this clear to everyone? Say yes or no in the chats. The value of net work done is coming out to be negative. That means net work is done by the gas, right? Perfect. Say yes or no in the chats quickly. Say yes or no in the chats quickly if this question is clear. It is a very simple and basic question, my dear students, which you can get from the cyclic process, yeah? Right? Perfect. Perfect, guys. Perfect. Moving on to one more question. Let's see if you can solve this or not. See, guys, I hope you can see the graph. Can you see the graph? A second. I think it's not properly visible, but I think you can, right? So you're starting from point A, then you are going from point A to point B. This is the first line, A to B, right? Then from B to C, right? And then from C to A. The arrows are towards, this is the first arrow, this is the second arrow, this is the third arrow, right? And at A temperature is given, B temperature is given, C temperature is given. And we are given with the pressure volume graph over here. First of all, you need to understand, before looking at the question, you need to understand whether the process is cyclic or not. Absolutely, the process is cyclic. The process is cyclic, right? It's a cyclic process. Yeah, number one. Number two, as per the question is concerned, 1 mole of an ideal gas. As far as the question is concerned, we have got 1 mole of ideal gas, which is monoatomic in nature. If the gas is monoatomic, its CV value has to be 3/2R. Its CP value has to be 5/2R. Now, as per the question, 1 mole of the ideal monoatomic gas is taken through the cycle shown below. Calculate AB and calculate CA. So we have to calculate QAB and then we have to calculate QCA. What is QAB first of all? Just try to understand. What is QAB? QAB is heat absorbed or released by the gas during the process AB. QAB, it is basically the heat absorbed or released by the gas during the process AB. What is this AB process? Is this AB process isochoric? Absolutely, it's isochoric, right? During the process AB, I would say volume of the gas is remaining constant. During the process AB, I would say volume of the gas is remaining constant. So what is QAB then? QAB represents heat released or absorbed by the gas at constant volume. QAB is heat absorbed or released by the gas at constant volume. And for the ideal gas, you know, that has to be equal to NCV delta T, which is T2 minus T1. Perfect. Similarly, we have to calculate QCA. What is QCA? Look at the process CA. Is the CA process isochoric or isobaric? CA process is isobaric. Pressure throughout this process is remaining the same, right? Pressure throughout the process is remaining constant. So this process is isobaric, right? So CA process is happening at constant pressure. So what is QCA then? It is the amount of heat absorbed or released by the gas at constant pressure, QP. And you must be knowing QP, that is basically equal to NCP T2 minus T1 for the ideal gas. I hope this is clear to everyone. Basically, I told you in the last session, heat absorbed or released by the gas at constant volume. That's basically delta U, right? That's basically delta U. So delta U for the process AB. Similarly, QP. QP is basically delta H, right? QP, heat absorbed or released by the gas at constant pressure. That's delta H, right? And delta H for the ideal gas, that's nothing. That's NCP delta T. Now, guys, look at the process AB carefully. Look at the process AB carefully. During the process AB, I would say this is the initial temperature. This is the final temperature. During the process AB, initial temperature, final temperature we calculated. Now, N value is given to us as the equation, that's 1. CV value for the gas is 3 by 2R, and it's T2 minus T1. 600 minus 300, that comes out to be 300, right? Perfect. So, this is 900 divided by 2, which comes out to be 450. So, the value comes out to be 450R. 450R. This is the value of heat. This is the value of heat. And the sign over here is coming out to be positive. If the sign is coming out to be positive, if Q value is coming out to be positive, that means during the process AB, heat is absorbed by the gas. And this much heat is absorbed by the gas during the process AB. Now talk about the process CA. Q for the process CA. That will be calculated through NCP T2 minus T1. Now in the process CA, during the process CA, during the process C to A, I'll say this is the initial temperature and this is the final temperature. Perfect. Now, N value, you know that's 1. CP value, that's 5 by 2R. And it has to be T2 minus T1. This is T2, this is T1. So 300 minus 450. The value comes out to be minus 150. Perfect. So it is going to be 5 into 150 comes out to be minus 750 R divided by 2. This is the value of Q during the process CA. So dear students, is the value of Q coming out to be positive or negative? It's coming out to be negative. If the value of Q during the process CA is negative, that means during the process CA, heat is released by the gas. And this much amount of heat is released by the gas during the process CA. Perfect. For example, you have to calculate QAB and QCA in calories. If it is to be calculated in calories, then put the value of R as 2 calories per Kelvin per mole. Put the value of R as 2 calories per Kelvin per mole. Right? So put the value of R as 2, the final answer will come out to be, it's going to be 900 calories. So this much amount of heat is absorbed during the process AB, right? Similarly, it's going to be R value 2 to cancel, the value is going to be minus 750 calories. So 750 calories of heat is released during the process CA. And these were the two things which we were supposed to calculate as far as the question was concerned. So let me know once in the chats if this is super clear to everyone, quickly. Quickly, my dear students, in the chats. Let me know quickly in the chats if all these things are clear. Whatever I told you till now. If all these things are clear, let me know quickly in the chats. Everyone. Everyone. Let me know quickly in the chats. Yeah? Perfectly done? Now, my dear students, look at this particular question and just try to analyze how exactly this sort of a question is to be solved. Let's try to understand. Let's try to understand how this sort of a question is to be solved. As far as this particular question is concerned, we are supposed to calculate Q net, W net, delta U net, and delta H net for this overall cyclic process. It's mentioned in the question that we have to take 1 ATM liter as 100 joules. R value, we have to take 8 joules per Kelvin per mole. And this particular cyclic process, it's valid for 1 mole of monoatomic gas. Try to understand exactly how this sort of a question is to be solved. Now, dear students, first thing, as far as the question is concerned, we are given with 1 mole of ideal gas. And the ideal gas is monoatomic in nature. So CV for the ideal gas is 3 by 2R. And CP for the ideal gas, that's 5 by 2R. Because the gas is monoatomic in nature, right? Now look at the graph carefully. Look at the process carefully. Is it cyclic? Is it cyclic? The initial state and the final state of the system is same. So absolutely it's a cyclic process. Absolutely it's a cyclic process. So whatever parameters we have discussed related to the cyclic process, all these things you can utilize over here in this particular question. Now, first of all, what are we supposed to calculate? If I ask you, what about delta U net for the cyclic process? Net internal energy change during the cyclic process. My dear students, as I told you a few minutes back, change in the value of a state function for a net cyclic process, that's always 0. So delta U net for the cyclic process, that has to be 0. Similarly, delta H net for the cyclic process, this again has to be 0 only. Something which we already discussed. Because U and H, they are the state functions. And change in the value of a state function for a cyclic process, that's always going to be 0. Right? Very simple and basic. Now at the same time, delta U, delta H for the cyclic process we have calculated. Now we have to calculate Q net and W net. Right? If I ask you what is Q net, you will say Q net means total heat absorbed or released by the gas during the cyclic process. Okay? So Q net has to be equal to QAB plus QBC plus QCA. Similarly, W net has to be equal to WAB plus WBC plus WCA. Now you must be thinking, why we have to calculate W net like this? Why can't we calculate area enclosed by the loop? Yes, students, you cannot calculate the area enclosed by the loop because it's not a triangle, it's not a square whose area you can easily calculate, right? Perfect. Now try to understand a few more things. First of all, at point A, the temperature of the gas is 400 Kelvin. Now the gas is changing its state from A to B. During the process AB, is the pressure remaining same? Absolutely, during the process AB, pressure is remaining same. Now, if you use the ideal gas equation, PV is equal to nRT, right? During the process AB, pressure is remaining constant. Number of moles of the gas, those are already constant. R is already constant. So volume has to be directly proportional to temperature. Now, at point A, what is the volume? 16 liters. At point B, what is the volume? 32 liters. That means when we go from A to B, is the volume of the gas doubling basically? Absolutely. And if the volume doubles, the temperature of the gas doubles too. Simple and basic. Yeah? On going from A to B basically, pressure is remaining constant, but the volume of the gas is doubling basically. This is the case of expansion, volume doubles. And if the volume doubles, the temperature automatically doubles, right? Temperature at point A was 400, so at point B, it has to be 800 Kelvin, right? Similarly, when you talk about B to C, during the process B to C, when the gas undergoes the process B to C, what happens exactly? When the gas undergoes the process B to C, what happens? Volume of the gas is constant. If volume is constant and already constant, I can say pressure is directly proportional to temperature. Now, when you move from B to C, what is happening to pressure? At point B, the pressure was 2 atm. At point C, the pressure is 1 atm. So from B to C, the pressure is reduced by half. If the pressure is reduced by half, can I say temperature will automatically reduce by half? Because pressure is directly proportional to temperature when volume is constant. If pressure becomes P by 2, that means temperature also has to become T by 2. So temperature over here was 800 Kelvin. So that means at point C, it has to be 400 Kelvin. Perfect. At point C, it has to be 400 Kelvin. Now, people, I would want you guys to understand a few important things now. During the process AB process, it's isobaric because the pressure is remaining constant. BC process, it's isochoric. Volume of the system is not changing. Volume of the gas is not changing, right? During the process CA, at point C, temperature was 400 Kelvin. At point A, the temperature again is 400 Kelvin. That means I'll assume that during this particular process, the temperature of the gas is not changing at all. And that particular process in which the temperature of the gas does not change at all, you'll be calling that as isothermal process. Now the graph is curved, so it has to be a reversible isothermal process. So CA process is reversible isothermal. So first of all, you identified your different processes over here. Okay. Now, dear students, let's try to analyze all these processes one by one. First of all, talking about the process AB. AB process. AB process is isobaric. The amount of heat absorbed or released during the process AB is QAB. This is the amount of heat absorbed or released during the process AB. But AB process, pressure is remaining constant, right? So heat absorbed or released by the process during AB, that will be equal to QP basically. During the process AB is isobaric. Pressure of the gas is not changing. So QAB is basically heat absorbed or released by the gas, constant pressure. That has to be equal to delta H for the process AB, which will be equal to NCP T2 minus T1. Or I'll write final temperature minus initial temperature. Perfect. Now calculate this QAB over here. QAB from this particular equation will come out to be N value is 1, CP value as per the equation. Since it's a monatomic gas, so CP has to be 5 by 2R. Final temperature minus initial, final minus initial. So value has to be 400. Value has to be 400. So what is the overall value which you'll be getting from here? 2, 1, 2, 2, 5, 2s are 10. So it's 1000 R. 1000 R. R value we have to take as 8. So it is 8000 joules. So we got to know the value of QAB basically. The value of QAB is coming out to be positive. That means during the process AB, heat is absorbed by the gas. And how much heat is absorbed by the gas? I'll say 8000 joules of heat is absorbed by the gas during the process AB. Perfect. Now similarly, my dear students, since I'm analyzing the process AB, so let's calculate WAB as well. Let's calculate WAB as well. Since the AB process is isobaric, and in case of isobaric processes, how do we calculate work? It's minus P delta V, which is simply V final minus V initial. So I'll start with minus. Pressure of the gas is simply 2 atm. V final minus V initial. V final is 32 liters. V initial is 16 liters. So 32 minus 16 comes out to be 16. The value comes out to be minus 32 atm liter. Now, as per the equation, they are telling you 1 atm liter is equal to 100 joules. So it has to be minus 3200 joules. Minus 3200 joules. This is the value of WAB as well. So you have analyzed the process WAB. Perfect. You have analyzed the process AB, in which you have calculated QAB, WAB. Perfect. Now, my dear students, it's time to analyze the process BC. It is time to analyze the process BC. Now, BC process, it's isochoric. It is isochoric. We have already discussed that. That means volume of the gas is remaining constant during the process BC. During the process BC, volume of the gas is remaining constant, right? If volume of the gas is remaining constant during the process BC, so what about WBC? If volume remains constant, WBC has to be 0, right? What about QBC? Heat absorbed or released by the gas during the process BC. Heat absorbed or released by the gas at constant volume. Basically QV. And QV is nothing, that's delta U for the process BC. And delta U for the ideal gas is nothing, it is NCV, T final minus T initial, right? Now calculate this QBC exactly how much it comes. N value 1. CV value for the gas is 3 by 2 R. R value we have to take as 8. T final minus T initial. During the process BC, this is T final, this is T initial. So 400 minus 800 comes out to be minus 400. This is minus 400. Calculate the value. It's 2, 1, 2, 4. 4 3s are 12. 12 4s are 48. So it's minus 4800 joules. So that means during the process BC, heat is released. When the gas is undergoing the process BC, heat is released. How much heat is released? 4800 joules of heat is released during the process BC. So BC process we have analyzed. WBC we have calculated, right? WBC we have calculated since it was isochoric, and QBC again we have calculated. Now there is one process pending, that is CA. Now look at the process CA. Look at the process CA. Is the CA process isothermal? That means during the CA process, whenever the ideal gas undergoes the process C to A, that means the ideal gas is undergoing a reversible isothermal process. And whenever the ideal gas undergoes a reversible isothermal process, or in general, whenever the ideal gas undergoes isothermal process, delta U for the ideal gas during that process, that has to be 0, something which we discussed in the last session. So delta U for the process CA, that has to be 0 because CA process isothermal in nature, right? So delta U CA will be nothing. It will be QCA plus WCA, because delta U is Q plus W. So delta U CA is QCA plus WCA. That has to be 0. So I would say QCA will be equal to minus times WCA. Perfect. So my dear students, just calculate one of the two. Just calculate one of the two. I'll try to calculate work done during the process CA. CA process is reversible isothermal. Do you remember how do we calculate work done in reversible isothermal processes? In the last session, I gave you one result, minus 2.303 nRT. It's log of V final divided by V initial, V2 by V1, if you remember. So WCA has to be equal to minus 2.303, N value is 1, R value is 8, Temperature is how much? 400 Kelvin. Perfect. And it's going to be log of V final divided by V initial. V final is 16 liters. V initial, that's 32 liters. So 16 by 32. 16 divided by 32. Now, solve it. Get the value of WCA, right? Let's assume that this is approximately, I'm taking as 2. So 8 2s are 16. 16 into 4 is 48. So it's minus 4800 log of 1 by 2. Log of 1 by 2. Log of 1 by 2 you can write as log of 1 by 2 you can write as log of 1 minus log of 2. Perfect. Log of 1 is 0 and log of 2 is 0.3. So WCA is coming out to be minus plus 4800 multiplied by 0.3 and the answer is going to be in joules. So this is the value of WCA. WCA you got. If you got WCA, that means QCA, you just have to reverse the sign. You just have to reverse the sign, right? So it's going to be minus times 4800 multiplied by 0.3 joules. This is the value of QCA as well. So you have analyzed all the process in detail. AB process you analyzed, BC you analyzed, then CA you analyzed. All the process you analyzed. Perfect. You got the value of QAB. You got the value of QBC, right? You got the value of QCA. Similarly, WAB, WBC, WCA, all the things you got. Now you have to put all these terms in this expression and get the value of QNet, which you were supposed to calculate. Similarly, put all the values of WAB, WBC, WCA in this expression and get the value of WNet, which you were supposed to calculate, right? The equation was a bit lengthy, no doubt, but I hope from this particular equation, you could understand it in a better way. Yeah? So let me know in the chats if all the things are clear till here. Quickly. Quickly, people. So I analyzed all the processes separately. I got QAB, QBC, QCA, then added them up, got the QNet. Similarly, I calculated WAB, WBC, WCA, and then added them up. I got the value of WNet. That's all. Yeah? Perfect, guys. Now there is one more important thing. Just a second. In cyclic process, there is one more small topic, and I would want you guys to clear that as well, right here only. That is efficiency of a cyclic process. How do we calculate the efficiency of a cyclic process? For example, I'm going to plot a graph over here. Pressure volume curve, P versus V. Okay. I'm starting from point A. I'm going from A to B. Then I'm going from B to C. Then, for example, I'm going from C to A. Arrow I'm showing towards right. Well, clockwise cycle. Perfect. This is the cyclic process. If I ask you to calculate the efficiency of this cyclic process, how do you calculate the efficiency of a cyclic process? Efficiency of the cyclic process is always equal. Efficiency of the cyclic process is calculated by the formula area enclosed by the loop. Area enclosed by the loop divided by area under the curve. Divided by area under the curve. Now, what is area enclosed by the loop? This is the area enclosed by the loop, right? That means which area I'm talking about? I'm talking about the area ABCA. ABCA, this area I'm talking about. Now, area under the loop, area under the curve, what that is? This is the total area under the curve. Let's say this is A, this is B, let's say this is E, let's say this is F. This whole area is the area under the curve basically, right? So, area under the curve will be basically the area ABEF. ABEF. ABEF, right? When you divide the two, you need to multiply this with 100 at the end. You'll be getting the efficiency of the cyclic process. Yeah? Now, let's do one question so that you'll understand it in a better way. So, a percentage efficiency of a cyclic process is always equal to area enclosed by the loop divided by area under the loop, under the curve, multiplied by 100. For example, this is the cyclic process which is given to us. This is the cyclic process which is given to us. Okay? We have to calculate the efficiency of the cyclic process. Efficiency of the cyclic process will be equal. Efficiency of this cyclic process will be equal to area enclosed by the loop. That means this area I'm talking about first of all. Area enclosed by the loop, which is going to be basically area of this particular triangle, which has to be half of base into height. Base is from here to here, which is 4 liters. Height is from here to here, which is 1 atm. So this is area enclosed by the loop divided by area under the curve. Area under curve, it means this whole area. Area under this curve. My dear students, this particular diagram, if you see, it is trapezium. How do we calculate area of trapezium? Half of sum of parallel sides. Sum of parallel sides, which is 1 plus 2. Half of sum of parallel sides into height. This is the height from here to here, 2 to 6, that means 4. Perfect. And at the end, you need to multiply it with 100. So numerator comes out to be 2. Denominator is 2 plus 1, 3, 3, 4, 12. 12 by 2 is 6. So 2 by 6 multiplied by 100. So efficiency of the cyclic process will be approximately 33%. Right? So this is basically how you calculate the efficiency of the cyclic process. Area enclosed by the loop divided by area under the curve multiplied by 100. Quickly, let me know in the chats if this is super clear to you. Then only I can start one more topic. Quickly, guys, everyone. Everyone in the chats, quickly. Everyone in the chats. Yeah? The loop was triangular in shape. So area enclosed by the loop was area of triangle. Area under the curve, that was area of the trapezium basically. Right? So area of the triangle divided by area of trapezium multiplied by 100. That's all. Perfect. Let me know, people in the chats, if all the things are clear till here. Let me know quickly in the chats with the thumbs ups, everyone. Everyone in the chats. Everyone in the chats. Yeah? Perfect, guys. So now let's try to discuss one more important topic, from which question again frequently comes. And what is the name of the topic? That's entropy. Right? You must have heard about it. Entropy. Entropy is represented by S. One is saying how to remember all these results, the way I have remembered them, by practicing many a times. That's it. Yeah. Make a separate formula sheet. Try to check them up 15 minutes every day. You'll remember all the formulas of the physical chemistry. Just try to make the formula sheets of physical chemistry basically. Okay. So entropy, which is denoted by S. My dear students, basically entropy is defined in two ways. There is first of all a mathematical definition of entropy, which I'll be discussing in some time. And there is one more way of interpreting entropy from its physical significance. There are two ways by means of which you can understand entropy. One way is to define the entropy mathematically. Another way is to understand the concept of entropy from its physical significance. So the second part I'm going to discuss first. Okay, so see, if I talk about entropy, it gives the measure of unavailable energy. It gives the measure of unavailable energy present in the system. Point number one. Point number two. It gives the measure of degree of randomness. It gives the measure of degree of randomness or disorderness present in the system. It gives the measure of degree of randomness or disorderness present in the system. More disordered the system, more disordered, or I'll say more random the system, more is going to be the entropy of the system. These are the 3 points which I would want you guys to remember first of all. What is the entropy? It gives the measure of unavailable energy present in the system. So basically, my dear students, for example, this is the gas in the container. For example, just to make you understand, this gas is my system, right? My dear students, in the system, actually, there are 2 types of energies. There are 2 types of energies present in the system, basically. One is called as available energy. One is called as unavailable energy. There are 2 types of energies basically present in the system. One is called as available, one is called as unavailable, right? This available energy, what is the use of this available energy? What is this available energy? I would say this available energy, it is converted into what? It is converted into useful work. Useful work is also called as non-PV work. Useful work is also called as non-PV work. Well, I'm not going to discuss about this right now. I'll be discussing this part, available energy part, I'll be discussing when I'll be teaching you the Gibbs free energy, not now. I'll have to discuss only this part right here, unavailable energy. This available energy I'll be discussing after some time when I'll be discussing Gibbs free energy with you. Okay. So first of all, a system always has 2 types of energies. One is available, one is unavailable. This available energy, it is converted into what? It is converted into useful work. Useful work is also called as non-PV work. What that is a separate debate, which we shall be discussing afterwards. The other type of energy of the system, that's unavailable. And what this unavailable energy in the system does, this unavailable energy in the system, it tries to increase the disorderness of the system. It tries to increase the randomness of the system. It tries to increase the randomness of the system. And that disorderness, that randomness present in the system is measured by the factor called as entropy. So basically, entropy, it gives the measure of unavailable energy present in the system. And this unavailable energy in the system, it tries to increase what? It tries to increase the disorderness of the system. It tries to increase the randomness of the particles present in the system. And that randomness is measured by the factor called as entropy. So what is entropy? Entropy is just a factor through which you get the idea about the degree of randomness, the degree of disorderness present in the system. Entropy is the factor through which you get the idea about the unavailable energy present in the system. So can I say, more the unavailable energy in the system means more random the system will be, more disordered the system will be, and more the disorderness of the system, you can say more will be the entropy of the system, right? So these 3 points which I discussed over here. More random or disordered the system, more is going to be the entropy of the system. That's all. Yeah. Now guys, just tell me one thing. For example, if I'll be having solid, liquid and gas under similar conditions, solid, liquid and gas. If I ask you to compare their entropies, can you let me know which system will be more random? Is solid, liquid or gas? Gas particles are more random than liquid, and liquid is more random than solid. More the randomness, more the disorderness, more has to be the entropy. So if solid, liquid or gas are present at similar conditions, so I must say solid gas will have maximum entropy, followed by liquid, followed by solid. Point number 1. Point number 2. If I talk about solids in particular, you have got 2 types of solids basically, right? One is called as crystalline solid, and one is called as amorphous solid. My dear students, do you remember we have discussed this in solid state? Crystalline solids have got ordered arrangement of constituent particles, and amorphous solids, they have got disordered arrangement of constituent particles. So if I compare the two, where is the disorder is more, crystalline or amorphous? I'll say amorphous has got more disorder. More the disorder, more the entropy. That's all. Simple and basic. Perfect. Now there are a few more things which I would want you guys to remember. What is that? See, whenever during the process entropy of the system increases, let's say during the process entropy of the gas, entropy of the system increases. If entropy of the system increases, that means change in entropy, which is going to be S final minus S initial. Final entropy minus initial entropy. If entropy of the system is increasing, that means final entropy of the system will be more. initial entropy of the system will be less. So this difference has to come as positive. Perfect. So whenever I say from now onwards that delta S for the system is positive, that means that the entropy of the system is increasing. Whenever I say change in entropy is positive, that means entropy of the system is increasing. And similarly, when the entropy of the system decreases, delta S, change in entropy, S final minus S initial, this value comes out be negative. So from now onwards, whenever I say that entropy change is negative, that means entropy of the system will be decreasing. If I say entropy change of the system is positive, that means entropy of the system is increasing. One more important point which you have to take a note of. Yeah. Similarly, guys, one more important point. As the number of atoms in a molecule, as the number of atoms in the molecule increases, the structure tries to become complex. The structure becomes complex. And when the structure becomes complex, energy states in the molecule basically increases, due to which disorderness increases. And hence, at the end, I must say, entropy increases. This is one more statement which I would want you guys to remember so that you can solve the questions which are based on the same statement. As the number of atoms in the molecule increases, entropy of the molecule increases because structure tries to become more complex. As complex the structure, more the complexity of the structure, more will be the energy states in the structure basically, right? And more the energy states means more is going to be the entropy, more is going to be the disorder. That's all. And where do I use these concepts? Let's try to understand. See guys, for example, you have got NO2 and N2O4. More the atoms, more complex the structure, more the entropy. So among these two, which will be having more entropy? N2O4. SO2, SO3, more the atoms in the molecule, more the entropy. CH4, C2H6. C2H6 will have more entropy because more atoms in the molecule. More atoms means more complex the structure, right? Similarly, these are few more questions. There are few more basic questions. What is the sign of delta S in the following reaction? Is the sign of delta S positive or negative? Look at the first example. As far as the first example, H2 gas is getting converted into 2 times H gas. This is my first reaction, in which H2 gas getting converted into 2 times H gas. Right here, the stoichiometric coefficient is 1. Right here, the stoichiometric coefficient is 2. So I'll say this 1 represents, it is 1 mole of H2. It gives 2 moles of H. 1 mole of H2 gives 2 moles of H. So during the process, are the moles increasing or decreasing? During the process, I would say the moles are increasing. If the moles are increasing, can I say the particles are basically increasing? And if particles increase, what will happen to the randomness? Randomness will increase, disorderness will increase, right? And if the randomness or disorderness increases, that means the entropy will increase. And when the entropy increases, delta S sign has to be positive. So in the first process, delta S sign will be positive, right? Talk about the second one. The second one is SO2 gas plus O2 gas. What is it giving me? It's giving me SO3 gas. First of all, write it in the balanced format. Now it's a balanced chemical equation, right? Now guys, have a look. This is 1 over here, this is 1 by 2. So 1 plus 1 by 2 makes it 3 by 2. And on the reactor, on the product side, this is 1. So I'll say 3 by 2 moles are giving us 1 moles. You have got 3 by 2 gaseous moles on reactant side. You have got 1 mole of gaseous products basically. So 3 by 2 is basically 1.5, correct? So 1.5 moles on the reactant side, 1 mole on the product side. So during the process, are the moles increasing or decreasing? The gaseous moles are decreasing basically. The gaseous moles are decreasing. Over here, gaseous moles were increasing. Right here, gaseous moles are decreasing. That means the number of particles will be decreasing, right? Particles will be decreasing. Disorderness will be decreasing. Entropy will be decreasing. That means delta S sign has to be negative. So in this process, the value of delta S has to be negative. Correct? Simple. Look at the third one. This is solid. This is gas. Solid is getting converted into gas. If solid is getting converted into gas, that automatically tells you that disorderness is increasing. If disorderness increase, entropy increase, delta is positive, right? Liquid into solid, delta is negative, entropy decreases, disorderness decreases. Diamond into graphite, diamond into graphite. In case of diamond, every carbon is attached to 4 other carbon atoms. In case of graphite, every carbon is attached to only 3 carbon atoms, right? So where is the randomness, disorderness more? Diamond is ordered, graphite is comparatively disordered. Ordered to disordered, ordered to disordered. That means disorderness is increasing, entropy is increasing. So delta S sign has to be positive, right? Now, on the reactant side, you have got gases. On the product side, you have got solid. On the reactant side, you have got gases. On the product side, you have got solid. So gas is getting converted into solid. If gases are getting converted into solid, gases have got more randomness. Solid, less randomness, less disorderness. So more disorderness towards less disorderness. That means during the process, disorderness is decreasing. Entropy is decreasing. If entropy is decreasing, delta S sign has to be negative. I hope all these things are absolutely clear to you. Yeah? Now, my dear students, you must be thinking, what happens to entropy of the egg when it is boiled? Right? When we boil an egg, what happens to its entropy? Quickly. My dear students, for example, I have got an egg over here and it's in liquid state. Now, what exactly I'm going to do? I'm going to heat it up. When I heat it up, this egg gets converted into solid. So basically, liquid is getting converted into solid. If liquid is getting converted into solid, more disorder to less disorder, right? More disorder to less disorder. That means disorderness is decreasing. Entropy should decrease, right? Entropy should decrease, but it is not happening. Entropy increases during this process. During the boiling of egg, entropy of the egg increases. Well, you know, if you talk about the egg, what is egg basically? It's a protein. What happens when you boil the protein? What happens when you heat the protein up? First of all, when you heat the protein up, the protein unfolds. When you heat it up, the protein unfolds, then refolds, and becomes a tangled structure. Right? That means, is the overall structure becoming complex during the process? During the process, I will say, overall, structure is becoming complex. And more the complexity of the structure, as I told you already, more is going to be the entropy. So during the process, the complexity of the structure is increasing. What does that mean? That means entropy will be increasing during the process. So during this process, entropy is increasing, so delta S sign has to be positive. Correct? When you heat the protein, first of all, the protein unfolds, then refolds, then becomes the tangled structure. So the complexity overall gets increased, due to which I'll say the disorderness gets increased. And if the disorderness increases, that means the entropy of the system increases. Yeah? All right, if I ask you, what happens to the entropy when you stretch the rubber? When you stretch the rubber, does the entropy increase or decrease? When you stretch the rubber, does the entropy increase or decrease? What do you think? What do you think? For example, on this side, I have got unstretched rubber. I'm taking unstretched rubber. Now I'm going to stretch it. So it becomes stretched rubber. It becomes afterwards stretched rubber. What will be the structure of the unstretched rubber? It will be a coil structure in the form of a coil. This is the structure of your unstretched rubber. When you stretch it, these coils, they get converted into linear shape. They attain the linear shape basically. Now you tell me which structure is complex, coiled or linear? This particular structure is complex. And if this particular structure is complex, more complex the structure, more the disorderness, more the entropy. So on this side, entropy is more, on this side, entropy is less. So when this process is happening, is the entropy increasing or decreasing? More entropy to less entropy. So I would say entropy of the system decreases. Therefore, delta S sign has to be negative. I hope this is clear to everyone. Yeah? Perfect. Perfect, guys. You have to remember all these things, right? Now, my dear students, there are few important characteristics of entropy which you need to know. Few important characteristics of entropy. The first one. If I talk about entropy, entropy is an extensive property. It is an extensive property. That means when you change the amount of substance present in the system, when you change the amount of substance present in the system, entropy of the system changes, right? Disorderness will change. Of course, when you change the amount of substance in the system, right? Disorderness will change, randomness will change. It will increase, decrease, whatever, right? So I would say entropy, it is that property whose value changes on changing the amount of substance present in the system. So it has to be extensive property. Now it is a state function as well. Entropy is a state function as well. So if you need to calculate change in entropy, how do you calculate it? Final entropy of the system minus initial entropy of the system. For any cyclic process, delta S has to be 0 because entropy is a state function, right? And change in the value of state function for a cyclic process, that always has to be 0. So delta S for the cyclic process, that will be always 0. I hope this is something which is clear to you, right? Right, people? Is it clear till here? All right. Now let me tell you one important thing. If I talk about universe, what is universe made up of basically? Universe is made up of system and surroundings, right? Universe is made up of system and surroundings. For example, if I ask you to calculate the total change in universe, total change in universe is represented by delta ST. Delta S total, it represents the total entropy change in the universe. Whatever will be the entropy change of the universe, that will be due to the entropy change of the system and due to the entropy change of surroundings. So first of all, we will have to calculate the entropy change of the system. Then we have to calculate the entropy change of the surroundings. We need to add them up, and eventually after adding them up, I'll be getting the total entropy change of the universe. So do remember this? These are the three questions which are asked basically. Calculate the entropy change of the system, calculate the entropy change of the surroundings, calculate the total entropy change of the universe, right? Universe is made up of system and surroundings. So whatever will be the entropy change in the universe, that will be due to the entropy change of the system and at the same time, the entropy change due to surroundings. Perfect. So we need to calculate the entropy change of the system first. Then we need to calculate entropy change of the surroundings. We need to add them up and we'll be getting the total entropy change of the universe. I'm telling you everything in a nutshell. You just have to remember all these, you can solve all the questions. Now, where do we use this particular concept? This is important, guys. This particular statement is important. Why is it important? You'll get the idea in some time. Okay, one more thing. Before dealing with this statement, there is one more thing. My dear students, how do you define the entropy change mathematically? How do we define the entropy change mathematically? For example, imagine that this is the container. It contains the ideal gas. It contains the ideal gas, okay? For example, I'm supplying dq amount of heat reversibly to this gas. This dq reversible is, for example, the amount of heat which is supplied to the system when the system is at temperature T. The system is at temperature T, right? This dq reversible I'm supplying to the gas. But do remember, whatever heat I'm supplying, it does not change the temperature of the gas. Whatever heat I'm supplying to the gas, it does not change the temperature of the gas. It is just used, for example, to change the randomness of the system, to change the disorderness of the system. So if I'm supplying heat to the system, there will be entropy change of the system. And that entropy change is represented by ds. And as per mathematical definition, it is always equal to dq reversible divided by T. dq reversible is the amount of heat absorbed or released by the gas reversibly when the gas is kept at a temperature T. This is the mathematical definition of what? Of entropy change. This is how you calculate small change in entropy. If I ask you how do we calculate the total change in entropy, you just need to integrate. Integration of dq reversible divided by T, right? This is how you calculate the total entropy change basically. Total entropy change. If you ask me what are going to be the units of this entropy, units of entropy, see in the numerator it's heat, in the denominator it's temperature. So one of the units can be joules per Kelvin, joules per degree centigrade, joules per whatever, right? Calories per degree centigrade, calories per Kelvin. You can use many units over here. Right, people? Yeah? Do remember, this is the gas which I took in the container. I'm supplying dq amount of heat to the gas. But the heat which I'm supplying to the gas, I'm supplying it in such a way that the temperature of the gas does not change. Only the heat which I'm supplying, it is just utilized to increase the randomness of the system. So if I need to calculate, due to the supplication, since I'm supplying heat, due to this heat supplying, what is going to happen? The disorderness will increase, right? So entropy will increase basically. And that change in entropy is represented by ds, which is calculated like this, dq reversible upon t, right? So total entropy change, you just have to integrate it. I hope this is clear to everyone. Now people, try to understand a few more things. See, there is something called a spontaneous, non-spontaneous process. Do you know what are spontaneous and non-spontaneous processes? What is a spontaneous process basically? That process which happens on its own. Number one, that process which takes place on its own, or just needs the initiation, That's something which you call a spontaneous, otherwise non-spontaneous. What it means and why am I telling you this right now? Before that, let's try to understand what a spontaneous process is. Any such process which happens on its own, which occurs on its own. For example, this is the object whose temperature is 100 Kelvin. This is one more object whose temperature is 1000 Kelvin, right? Now, for example, if I bring them in contact, what will happen? If I bring these two in contact, what is going to happen? Since there is temperature difference, due to temperature difference, heat will automatically flow from higher temperature to lower temperature. So flow of heat, it is happening on its own, right? Any such process which happens on its own, that's what you call as that's what we call a spontaneous process. For example, flow of heat, right? Flow of heat, it happens on its own. It is a spontaneous process, right? Burning of kerosene. If I define the process, burning of kerosene. My dear students, you have kerosene, for example, right? You just need to give it a flame, right? If you give flame to kerosene, it will automatically burn. So you are just initiating the process. Rest, everything is happening on its own. You are just initiating the process. Rest, everything is happening on its own. So this one is completely happening on its own. This process, it just needs to, we need to initiate the process. Rest, it will happen on its own. And any such process, which either completely happens on its own or needs a proper initiation, right? That's what we call as spontaneous process. Perfect. Now, my dear students, the point is very simple. See what the point is. If entropy is the only criteria, to check whether the process is spontaneous or not, what do we do at that point of time? If entropy is the only criteria, to decide whether the process is spontaneous or not, then, my dear students, you have to remember a few things. Do remember, if delta is total, which is the entropy change of the universe, if delta is total due to the process, if it comes out be positive, then we say the process is spontaneous and irreversible. Second point, if delta is total comes out being negative, we say the process is non-spontaneous. And at the same time, if delta is total comes out be 0, we say the process, it is reversible, or you can say system and surroundings are at equilibrium. System and surroundings are at equilibrium. You can say something like this as well. So do remember, if entropy is the criteria to check whether the process is spontaneous or not, you have to calculate delta as total. Change in the entropy of the universe. If it comes out to be positive, the process is spontaneous. If it comes out to be negative, non-spontaneous. If it comes out to be zero, that means it is reversible, or you can say the system and surroundings that are at equilibrium. So these are the three conditions which I would want all of you to remember from now on, right? So for reversible processes, delta as total will be zero. For irreversible processes, delta as total is greater than zero. Do remember this particular thing as well. Yeah. Now guys, entropy, it's not done yet. We have to discuss a few more things about entropy. What is that? Have a look. I'm marking the heading as entropy change. Entropy change when an ideal gas. Entropy change when an ideal gas undergoes a change in state. Entropy change when an ideal gas undergoes a change in state. What does it mean? Have a look. For example, you have got ideal gas in the container. Let's say the ideal gas is undergoing expansion. Ideal gas is undergoing compression. Ideal gas is simply undergoing a change in state. During the change in the state, entropy of the gas will change. Now, how do we calculate the change in the entropy of the ideal gas when it undergoes a change in state? That is our topic basically. Try to understand how exactly I'm going to get the result over here. This is important. This is important. Try to understand this. For example, this is the gas in the container. This is the ideal gas in the container, for example, right? Let's say we are supplying dq amount of heat reversibly to this gas, which is at temperature T. Since we are supplying dq amount of heat to the gas, there will be entropy change of the gas. That entropy change of the gas I'm representing with ds. So ds has to be equal to dq reversible upon temperature, right? Perfect. Now, my dear students, for example, what exactly I'm doing? For example, I have got a gas. This is the gas over here. This is the ideal gas over here. Perfect. For example, the initial volume of the ideal gas is V1. The final volume of the ideal gas is V2. The initial temperature of the ideal gas is T1. The final temperature of the ideal gas is T2. Let's see exactly after changing these parameters, what would have happened to the entropy of the gas, right? Let's get to know on changing the volume, on changing the temperature, right? What happens to the entropy of the gas? So let's try to understand. First of all, we need to calculate the total entropy change of the gas, which undergoes a change in state. So basically, we need to calculate the value of delta S, which is integral dq reversible upon T. Right? We need to calculate the total change in the entropy of the gas, which is undergoing a change in state, whose volume is changing from V1 to V2, whose temperature is, for example, changing from T1 to T2. Now, if I ask you, as per first law of thermodynamics, delta U is equal to Q plus W. So du is equal to dq plus dw. So from this, can't you calculate dq? dq has to be equal to du minus dw. So my dear students, in place of dq, what I'll be writing? In place of dq, I'll be writing du minus dw. Divided by what? Divided by temperature. So I'll say delta S is equal to integral. What is du? Small change in internal energy for the ideal gas. So du is nothing, it is NCV dt divided by temperature. There is a sign minus in between, right? There is a sign minus in between. Integral of. What is dw? dw is minus pdv, minus plus. It is pdv divided by temperature. Something like this. Perfect. Now here you are integrating with respect to temperature. Temperature is changing from T1 to T2. Here you are integrating with respect to volume, right? And volume of the gas is changing from V1 to V2. Correct till here? I hope till here it's clear. Now try to understand what exactly I'm going to say. Just a second. Try to understand what exactly I'm going to say. Right? First of all, dear students, understand properly what I am going to say. I'll write delta S is equal to N I'll take out, CV I'll take out. Integral of dt by t. First of all, it's going to be N CV. Integral of dt by t, it's ln of t, upper limit, lower limit. So it's going to be ln of t2 divided by t1. In the middle, the sign is positive, right? Now over here, you have got p by t. You know, PV is equal to nRT. PV is equal to nRT. So can I say P divided by T is equal to nR by V? Absolutely, P by T is equal to nR by V. And over here, you have got P by T. So instead of P by T, what you can write? Instead of P by T, you can write nR divided by V, and dV is already there. Yeah. So over here, I'll be getting the final result, which I would want you guys to remember. This NCV ln of T2 divided by T1 plus nR will come out because constant both. Integral of dy by v is ln of v. So upper limit, lower limit. So ln of v2 divided by v1. So my dear students, this is the first expression which I would want you guys to remember. First expression which I would want you guys to remember to calculate the entropy change of the ideal gas which undergoes a change in state. Yeah. This is how you calculate entropy change of the gas, of the ideal gas, which undergoes a change in state. Okay. This is the first expression. Similarly, the second expression. Understand the second expression. My dear students, in states of matter, I had given you one equation, combined gas equation. P1 V1 divided by P2 V2 is equal to N1 T1 divided by N2 T2. Since, if you remember a few minutes back, I took a container in which a gas was present, right? Was there any leakage or something? There was no leakage or something, right? Was I introducing some extra gas in the container? No. So number of moles of the gas were fixed. If the number of moles are fixed, if the number of moles are constant, so remove N1 and N2. So I'll be getting P1 V1 divided by P2 V2 is equal to T1 divided by T2. Perfect. So I'll be getting something like this. P1 divided by P2 multiplied by T2 divided by T1 is equal to V2 divided by V1. Do you agree with this? Right? V2 here, V1 here. So V2 by V1 is this value. And in this particular expression, do you see you have got V2 by V1 here? So instead of V2 by V1, I'm going to introduce few more terms. So delta S gas has to be equal to NCV, ln of T2 divided by T1, plus NR, ln of, instead of V2 by V1, I'll be writing P1 by P2 multiplied by T2 divided by T1. I hope this is clear. I hope this is clear to you. I hope this part is clear. Yeah. All right. Now it's just a matter of calculation. So I'll say delta S for the gas is equal to NCV ln of T2 divided by T1 plus NR. It is ln of M into N. Ln of M into N, which is ln of M plus ln of N. Perfect. Now, dear students, one more thing which you can do. Say ln of T2 by T1, ln of T2 by T1. You can take common. You can take N common. So delta S gas. Delta S gas is equal. N you have taken common. Ln of T2 by T1 you have taken common. Over here you have got CV, over here you have got R. So CV plus R comes out to be CP. So it's NCP ln of T2 divided by T1 plus NR ln of T1 divided by P2. So this is one more equation which I would want every one of you to remember to calculate the entropy change of the ideal gas which undergoes a change in state. So these are the two expressions which I would want every one of you to remember. NCV ln T2 by T1 plus NR ln V2 by V1. NCP ln T2 by T1 plus NR ln P1 by P2. Right? Now, my dear students, where do we use these expressions? Have a look. For example, an ideal gas. Let's say you have got an ideal gas undergoing isothermal process. If you have got an ideal gas undergoing isothermal process, how do we calculate its entropy change? Entropy change of the ideal gas, which is undergoing isothermal process. In case of isothermal process, temperature is constant. If temperature is constant, T1 will be equal to T2. If T1 is equal to T2, this term becomes 1. Ln of 1 is 0. So this whole term becomes 0. So the formula will be NR ln of V2 by V1. NR ln of V2 divided by V1. So whenever an ideal gas undergoes an isothermal process, this is how you calculate entropy change of the ideal gas. Point number 1. Yeah. Point number 1. Right. Now, my dear students, whenever an ideal gas undergoes isochoric process. Okay, one more result. Wait, one more result. In isothermal, one more result. Isothermal temperature is constant. T1, T2 is same. So this gets cancelled out. Ln of 1 is 0, right? This term is 0. It can be nR ln of P1 by P2. It can be nR ln of P1 divided by P2. Correct? These are the two expressions which you can remember to calculate entropy change of the gas which undergoes isothermal process. Now, if the ideal gas undergoes isochoric process, so volume is constant, V1 is equal to V2. If V1 is equal to V2, gets cancelled out, ln of 1 is 0, this term is 0, so it's going to be NCV ln T2 by T1. NCV ln T2 divided by T1. This is your delta S gas. When the gas undergoes what? When the gas undergoes isochoric process. Yeah, when the gas undergoes isochoric process. Perfect. When the gas undergoes isochoric process. Now similarly, if the gas undergoes isobaric process, if the ideal gas undergoes isobaric process, that means pressure is constant. If pressure is constant, that means P1, P2 are same. So this term becomes 0. Finally, it's going to be NCP ln T2 by T1. NCP ln of T2 divided by T1. This is how you calculate entropy change of the gas, which entropy change of the ideal gas, which undergoes isobaric process, right? Now the point is, if the ideal gas undergoes adiabatic process, then you'll be using either this relation or this particular relation completely to calculate the delta S for the ideal gas, which is undergoing adiabatic process, right? Perfect, clear? Is this clear to here, people? Quickly. These two results are used for adiabatic process as well. These are the general expressions, okay, which you can utilize for adiabatic processes. I hope all these things are clear. And if all these things are clear, let's try to solve few questions so that it becomes absolutely clear to you. Okay, this is the first question. Try to understand what the question says. 1 mole of ideal monoatomic gas. You have got 1 mole of ideal gas which is monoatomic in nature. So CV is equal to 3 by 2R. That means CP will be equal to 5 by 2R. So 1 mole of ideal monoatomic gas was taken through isochoric heating. So the ideal gas is undergoing isochoric process. Ideal gas is undergoing isochoric process from 100 Kelvin to 1000 Kelvin. Initial temperature of the gas is 100 Kelvin and final temperature of the gas is 1000 Kelvin. Calculate delta S system, delta S surrounding and delta S total if the process is carried out reversibly. Few minutes back I told you, if you remember, delta S total in case of reversible process, that is 0. Delta S total for a reversible process, that is 0. If delta S total is 0, that means delta S system plus delta S surrounding. Delta S system plus delta S surrounding, that has to be 0. So what does that mean? That means delta S system has to be equal to minus times delta S surrounding. Perfect. Delta S system has to be equal to minus times delta S surrounding. See, delta S total you have calculated. Now calculate delta S system. Delta S system means delta S gas. Delta S gas, which undergoes isochoric process. In case of isochoric processes, when the ideal gas undergoes isochoric process, what is the formula? NCV ln T2 by T1. NCV ln T2 by T1. So it's NCV ln of T2 divided by T1. N value is 1. CV value is 3 by 2R. Let's say we have to calculate everything in calories. So put the value of R as 2. NCV 3 by 2R. Ln of T2 by T1. 1000 by 100 is 10. Right? And ln of 10 is 2.303. So this got cancelled. So 3 multiplied by 2.303, which comes out to be 6.909. It's going to be calories per Kelvin. So this is the entropy change of the system. This is delta S system, this is delta S gas. If delta S system you calculated, so delta S surrounding. Delta S surrounding has to be equal to minus times 6.909 calories per Kelvin. Delta S system you calculated, delta S surrounding you calculated, and delta S total will be automatically 0, right? This plus this will come out to be 0. It is just their sign is different. Let me know once in the chats if it's clear. Let me know once in the chats if it's clear, quickly. Okay, let's try out one more question. This is one more question. The question is 1 mole of an ideal gas, 1 mole of an ideal gas, which is diatomic in nature. So Cv is equal to 5 by 2R, Cp is equal to 7 by 2R. So 1 mole of ideal diatomic gas was heated at constant pressure of 1 atm. Was heated at constant pressure of 1 atm to double its temperature. So initial temperature is, for example, T. The final temperature of the gas is 2 times T. Okay. At constant pressure. At constant pressure means the process is isobaric in nature. We are heating the ideal gas at constant pressure. If the temperature of the gas initially was 27 degrees centigrade, okay, initial temperature is given as 300 Kelvin. What does that mean? Final temperature will be equal to 600 Kelvin because you are doubling the temperature. Calculate delta S system, delta S surrounding, delta S total. If the process is carried out reversibly, right? Since dear students, it's again the reversible process. In case of reversible processes, delta S total has to be 0. In case of reversible processes, delta S total has to be 0. What does that mean? That means delta S system, which is basically delta S gas, will be equal to minus times delta S surroundings, right? So delta S system has to be equal to minus times delta S surroundings. Now calculate delta S for the gas which undergoes. Delta S for the system, delta S for the gas, which undergoes isobaric process. What is the formula we use in case of isobaric processes? In case of isobaric processes, this is the formula which we use. NCP ln of T2 by T1. NCP ln of T2 by T1. So NCP ln of T2 divided by T1. Now what is the value of N? That's 1. CP value. CP value, that's 7 by 2R. 7 by 2, take the R value in calories, right? Ln of T2 divided by T1. T2 is 600, T1 is 300. So 600 divided by 300 comes out to be 2, right? Which can be mentioned as 7 ln 2, right? Ln 2 is approximately 0.7. So it comes out to be 4.9 calories per Kelvin. So this is the value of delta S for the gas which is undergoing isobaric process, which is undergoing reversible isobaric process. Now, what about delta S surroundings? Delta S surroundings has to be equal to minus times delta S system. So it's minus times 4.9 calories per Kelvin, right? This is how you calculate delta S surroundings over here. And my dear students, one thing, I'm only calculating for the reversible process. In your NEET, they do not ask you for the irreversible processes. That's for JE basically, right? For JE, the questions about entropy, they become comparatively difficult when you have to do the entropy calculation for surroundings, for irreversible process, right? That becomes comparatively difficult. But in your NEET, they'll be only asking you about the reversible process, not the irreversible ones, right? Perfect. Someone is asking, sir, how to calculate CV? Wow, I think you're very late. Go and watch the first 2 sessions of thermodynamics. Okay, guys. Now, there is one more topic related to entropy. What is that? That is entropy change. Entropy change during reversible. Entropy change during reversible heating or cooling. Entropy change during reversible heating or cooling of a solid or a liquid. Of a solid or liquid. This is one more topic related to entropy, and this is simple, right? It's not that lengthy also. See what exactly it means. See what exactly it means. Understand? My dear students, for example, imagine that this is the solid which we have. XS. This X is a solid. Okay? This X is a solid. I'm supplying some heat to the solid. For example, I'm supplying this much of heat. dQ, reversible amount of heat to the solid. Right? Initially, the temperature of the solid is T1. Finally, the temperature of the solid is T2. What am I doing? I'm supplying heat to the solid. Right? But I'm supplying heat to the solid. Okay? But making sure that the state of the substance is not changing. Only the temperature of the substance is changing. I'm supplying, for example, heat to the solid. Okay? Due to which the temperature of this solid is changing. Perfect. Now, since we are supplying heat to the solid, whose temperature is changing from T1 to T2, its entropy will automatically change. How do we calculate that change in entropy? You know it. How do we calculate that change in entropy? Entropy change is generally calculated like this. Integral of dq reversible upon T. This is the general expression, if you remember. This is the general expression. And my dear students, we are increasing the temperature. We are changing the temperature from T1 to T2. This is the general expression which you'll be using. Right? Now, there are many ways by means of which we can calculate dq. I have told everything in detail, if you remember. If heat capacity is given, then dq is equal to c dt. If specific heat capacity is given, then dq is equal to ms dt. If cv is given, then it's ncv dt. If cp is given, then dq is equal to ncp dt. Right? Now, as per question, you just have to place the value of dq. If in the question they are given with the heat capacity, then instead of dq, you have to write c dt. Right? Mentioning that if T is given, if heat capacity of the substance is given, perfect, then delta S for the substance has to be equal to integral from T1 to T2. dq is going to be c dt divided by T. Right? By chance, if specific heat capacity of the solid is given, whose temperature you are changing from T1 to T2, then delta S has to be equal to integral T1 to T2. It's going to be ms dt divided by T. Right? Similarly, for example, if molar heat capacity at constant volume for the substance is given, then delta S has to be equal to integral T1 to T2. It's going to be n cv dt divided by T. Similarly, delta S has to be equal to n cp dt divided by T. So basically, depending on what are the parameters that are given to us as per the equation. If C is given, use this particular result. If S is given, use this particular result. If CV is given, use this particular result. Right? Perfect. But do remember, this is basically how we calculate entropy change of a solid or a liquid whose temperature we are changing from T1 to T2, irrespective of changing their state. Right? All these things are valid for liquid as well. For example, you have got X liquid. You are supplying some heat. It is becoming X liquid only. Only its temperature is changing from T1 to T2. You can use all this procedure for this particular substance as well. Yeah? Let's try to solve one question from this so that we'll get the idea. What kind of question can be asked from this one? Have a look. Understand. For a 1 mole of perfectly crystalline solid. So you have got, for example, 1 mole of X, which is perfectly crystalline solid. Right? For a 1 mole of perfectly crystalline solid, Cp is equal to 80, where A is this. If Cp is equal to 4.2 kilojoules at 10 Kelvin, then calculate the change in entropy when it's heated from 10 Kelvin to 20 Kelvin. So basically, as per question, initial temperature of the solid is 10 Kelvin. Now you are heating it up. You are heating it up. Its temperature now is becoming 20 Kelvin. So you are changing the temperature of the solid from 10 Kelvin to 20 Kelvin. There will be definitely the change in its entropy, right? There will be definitely change in its entropy. So that change in entropy we have to calculate, which has to be integral T1 to T2, dq by dt, dq by dt. Check what is given. Cp is given. So instead of dq, you'll be writing ncp dt divided by T. This is the formula which you have to use. This is the formula which you have to use, number one. Number two, as per the question, it's mentioned that Cp is equal to A times capital T, right? Where A is a constant. And it's mentioned that Cp value is 4.2 when temperature is 10 Kelvin. Cp value is 4.2 when temperature is 10 Kelvin. So you can calculate A from here. So A is coming out to be 0.42. So you calculate A, right? So dear students, the question is almost done. It's from 10 to 20. Number of moles is 1. 1 mole of gas is given. Cp value is given to us as A times capital T. So this is dt divided by T. So T and T got cancelled. So it's going to be integral from 10 to 20, right? A will come out, right? dt will remain as such. So it's going to be A times integral of dt is T, upper limit, lower limit, right? So it's going to be 20 minus 10. Now A value is 0.42 multiplied by 10. So the value has to be 4.2 joules per Kelvin. This is the value of delta S. Correct? Is this question solved? Done and dusted? Simple. Whatever results I'm giving you, I'm utilizing all these results. That's it. Nothing else. I'm doing nothing new here. I'm doing nothing new here. I'm doing nothing new here. Just let me know once in the chats if every single thing is clear to them. Yeah. It is just for solids and liquids we use the integral. When we talk about the gas, when the gas is undergoing expansion, compression, or when the gas is undergoing a change in state, then direct results which I gave you, those 3-4 results for isothermal, isobaric, adiabatic, etc. Yeah. Perfect. And all those results which we gave, which we derived them by doing integration only, right? Let me know once in the chats if all the things are clear till here. The last topic of your chapter, that's Gibbs free energy. It's again one of the important topics. Okay. And it's a bit lengthy as well. So, but we'll be starting exactly from basics itself. Yeah. Gibbs free energy. Gibbs free energy, or you can call it as Gibbs function, which is denoted by capital G. Gibbs function, Gibbs free energy, which is denoted by capital G. My dear students, first of all, what was the need to introduce this G? What is the need to introduce this new function? Why is that? A few minutes back, I told you, in order to check whether the process is spontaneous or not, what do we have to do? We have to calculate the value of delta ST. If the delta S total is greater than 0, that means the process is spontaneous. What is delta S total? It's delta S system plus delta S surroundings. This has to be greater than 0. Then only I can say the process is spontaneous, right? If entropy is the criteria for spontaneity, then we have to calculate delta S system first. Then we have to calculate delta S surrounding also. Then we have to sum them. We have to add them. If the sum comes out to be greater than 0, then only we can say the process is spontaneous, right? But my dear students, if I keep Gibbs free energy as the criteria for spontaneity, you have got nothing to do with the surroundings. You just have to do the calculation of system. You just have to do the calculations related to system. So over here, if entropy is the criteria for spontaneity, then you have to calculate delta S system, then delta S surrounding, then add them up. Then you can say whether the process is spontaneous or not. So basically, calculations are lengthy here. First delta S system, then delta S surrounding, then add them up, right? So the calculations are lengthy. So in order to reduce these calculations, a new function was introduced, which is what you call as Gibbs function. Which is denoted by G. And G is equal to H minus Ts. H is enthalpy, T is temperature, S is entropy. G is equal to H minus Ts. If you remember, the way we introduced H was U plus PV. U plus PV we called as H. And similarly, H minus Ts will be directly calling as G, Gibbs function. Right? So, by introducing the Gibbs function, what happens? You have got nothing to do with the surroundings now. If you want to check whether the process is spontaneous or not, you just have to calculate change in the Gibbs free energy of the system. That's all. How exactly you'll get to know in some time. Just wait for it. See, first of all, G is equal to H minus Ts, right? So if I multiply throughout by D, it is dG is equal to dH minus d of Ts, right? So you can write it as dG is equal to dH minus, it is TdS minus S dt. If I write the same equation at constant temperature, at constant temperature, change in temperature will be 0. So dG has to be equal to dH minus T ds. Because dt is 0, so this term becomes 0. Perfect. So just integrate all. If you integrate all, it becomes delta G is equal to delta H minus T delta S. This is the equation, first of all, which I would want every one of you to remember for the calculation of delta G. Change in the Gibbs free energy is always equal to delta H, enthalpy change, minus temperature, multiplied by delta S, entropy change. This is the first equation which I would want you guys to remember, right? Number one. Number two. This Gibbs function gives free energy. What about its physical significance? What kind of idea it gives us? You'll get the idea in some time. But before that, there is something important. This G is an extensive property. Gibbs free energy, it's extensive property. It's a state function as well. For a cyclic process, change in the value of Gibbs free energy will be 0. For the cyclic process, change in the value of Gibbs free energy, that will be 0, right? Now comes the point. Now comes the point. If Gibbs free energy is the criteria for spontaneity, if Gibbs free energy is the criteria for spontaneity, then do remember, for the process to be spontaneous, delta G for the system at constant pressure and temperature, delta G for the system at constant pressure and temperature, it has to be negative. Then only I can say the process is spontaneous. Then only I can say the process is spontaneous. Similarly, if delta G for the system at constant pressure and temperature comes out to be greater than 0, we'll be saying the process is non-spontaneous. Non-spontaneous. And similarly, if delta G for the system at constant pressure and temperature, if it comes out to be 0, then you will say system and surroundings, they are at equilibrium. So my dear students, understand one thing. If entropy was the criteria for spontaneity, you were supposed to calculate delta S system, then delta S surrounding. But if Gibbs free energy is the criteria of spontaneity, you just have to calculate delta G for the system. By just calculating the delta G for the system, you can check whether the process is spontaneous or not. You do not have to calculate delta G for the surroundings, unlike entropy. Right? In case of entropy, we are supposed to calculate delta S surrounding as well. But here, we just have to calculate delta G for the system at constant pressure and temperature. If you get the delta G for the system at constant pressure and temperature by just having a look at their values, you can get to know whether the process is spontaneous or not. Yeah? Okay, so do remember these 3 cases. These are really, really very important. These are really very important. Before talking about the significance of this Gibbs function, before talking about the significance of Gibbs free energy, what is it exactly? Before talking about that, let me give you a few more things. See, I told you delta G is equal to delta H minus T delta S. Correct? This is something which I told you. Delta G is equal to delta H minus T delta S. Now guys, over here I'm mentioning delta H. Right here I'm mentioning delta S. Right here I'm mentioning delta G. Okay? For example, the first case. If you have got a process whose delta H is coming out to be negative, any process whose delta H is negative, delta S is positive. For example, you have got any process whose delta H is negative, delta S is positive. This term is negative. This term is positive. Positive negative is negative. So the overall sign of delta G will come out to be negative. And when delta G comes out to be negative, we'll say the process is spontaneous. It is spontaneous at all temperatures. At all temperatures. Perfect. So basically what it means, delta H negative means exothermic. Energy is released. Energy is released. So during the process, energy is released. The system is going towards low energy. If the energy is released during the process, energy possessed by the system is decreased with time. Right? And you know, as far as the energy factor is concerned, system always tries to go in that direction in which the energy decreases. Right? Let me write these 2 statements first of all. System tries to move in a direction in which energy decreases and entropy increases. System always tries to move in a direction in which energy decreases and entropy increases. Now guys, delta H is negative, so energy is released. If energy is released by the system, energy possessed by the system decreases with time. So energy is being decreased. Now similarly, delta S is positive, so entropy of the system is increasing. So energy of the system is decreasing, entropy of the system is increasing. So both the things are favorable here. Both the things are favorable. So automatically the process is going to be spontaneous. Right? If you have got a process A to B, let's say we have to check whether this process is spontaneous or not. If during this process energy of the system is decreasing, entropy of the system is increasing, then only you can say the process will happen. Then only you can say the process will happen. The process will be spontaneous, whose delta G will be negative. Anyways, leave that part aside. Not going to talk about it in detail. Second thing, I'm just going to tell you the things which are needed, right, for the question solving. Second thing, if for example, delta H is positive, if for example, delta H is positive and delta S is negative, if this term is positive and this term is negative, negative makes it positive, and over here it was already positive. So this whole term, delta G, is coming out to be positive. And you know, when delta G is positive, I'll say the process will be non-spontaneous under all conditions. Non-spontaneous at all temperature. Okay. Now guys, third case. If for example, delta H is negative, if delta H is negative and delta S is also negative, delta H is negative, delta S is negative, negative is positive. So this term is negative. In the middle, you have got positive. This term is for example negative. In the middle, it's coming out to be positive. So when can be the overall delta G negative? Overall delta G can be only negative if the magnitude of delta H will be greater than that of magnitude of T delta S, which is only possible at low temperatures. At low temperatures. So I would say any such process whose delta H is negative, delta S is negative, the process will be only spontaneous at low temperatures. Okay. Similarly, the fourth case. For example, the first thing is positive and second thing, delta S is also positive. Delta H is positive, right? Delta S is also positive. This is positive, this is positive. Positive, negative is negative. So the overall term, when it will come out to be negative, the overall term delta G will come out to be negative only if the magnitude of T delta S is greater than that of magnitude of delta H, which is only possible at high temperatures. So I must say any such process whose delta H is positive, delta S is positive, the delta H value will only come out to be negative. The process will be only spontaneous at higher temperatures. That's all what you have to remember. I hope this is clear to everyone, right? My dear students, for example, I'm giving you one small question out of it. Let me see if you can solve this or not. A small question like this. Let's say you have got a process A gives B. Delta H is, for example, minus 80 kilojoules. Delta H is, for example, minus 80 kilojoules. And delta S is, for example, 2 times capital T, joules per Kelvin per mole. We have to check the temperature at which the process will be spontaneous. Calculate the temperature at which the process will be spontaneous. At what temperature the process will be spontaneous? What is the criteria for spontaneity? For the process to be spontaneous, delta G for the system at constant pressure and temperature, it has to be negative. So delta H minus T delta S, this has to be negative, right? What is delta H? Minus 80 kilojoules. So minus 80,000 joules, less than. This T delta S will come on that side. It's T, delta S value is 2 times capital T. Perfect. So what I can say over here, just a second. This minus, just a second. So make it positive. So this is plus 80,000 less than. So 80,000 is coming out to be less than 2T square, or you can say 2T square is greater than 80,000, or you can say T square is greater than 40,000, or I can say T is greater than 200 Kelvin. So what is meant by this particular thing? Check it out. I gave you one process whose delta H is given, whose delta S is given. I'm telling you to calculate, I'm asking you to calculate the temperature at which the process will be spontaneous. For the process to be spontaneous, delta G for the system at constant pressure and temperature, it has to be negative. So delta H minus T delta S, it has to be negative. When you do the calculation, finally you are getting temperature should be greater than 200 Kelvin. So temperature has to be greater than 200 Kelvin, then only the process will be spontaneous, right? Is this clear to everyone? Quickly? We are going to do a few more questions about this, but before that, we have to talk about a few more concepts related to Gibbs free energy so that you can get to know about its physical significance. And before talking about the physical significance, there is one thing which I forgot to tell you related to entropy. What is that? There is one thing which I forgot to tell you related to entropy. So let me just finish that statement. What is that? Have a look. I'm mentioning, first of all, entropy change during the reaction. How do you calculate the entropy change during a reaction? It's a very simple thing. Entropy change during the reaction. Then I'll move to the Gibbs free energy again. Okay, this is something which I skipped in between. I forgot this. For example, you have got the reaction N1A plus N2B. Let's say it gives N3C plus N4D. This is the reaction, for example. I want you guys to calculate the entropy change during the reaction. Entropy change during the reaction is nothing. It is entropy of product minus entropy of reactant. And how you guys are going to write it? Entropy of product. This is my product, this is my product. Stoichiometric coefficient of C is N3. N3 multiplied by entropy of C plus N4 multiplied by entropy of D. So this is your overall entropy of products minus entropy of reactants. Entropy of reactants. Stoichiometric coefficient is N1. N1 multiplied by entropy of A plus N2 multiplied by entropy of B. In the question, if they give you entropy of C, entropy of D, entropy of A, entropy of B, you can easily calculate entropy change of the reaction. Yeah? You can calculate entropy change for the reaction. Perfect? So do remember this particular thing by means of which you can calculate entropy change of the reaction. Perfect? Even you can calculate entropy change under standard conditions as well. Sometimes they'll give you the entropy of A, B, C, D under standard conditions, and they'll ask you to calculate the standard entropy change of the reaction. You can write this in this way. That's all. Okay? You'll see its application as well, but in some time. So what we were discussing, basically, we were discussing about Gibbs free energy, right? We were discussing about Gibbs free energy. Now, just a second. Okay. Let's talk about this particular equation. The molar entropy of X2, Y2 and XY3 are 60, 40 and 50 for the reaction this, whose delta H is given. The process will be spontaneous at. For the process to be spontaneous, delta G for the system at constant pressure and temperature has to be less than 0. So delta H minus T delta S has to be less than 0. So delta H has to be less than T delta S. Or I'll say T delta S has to be greater than delta H. Or I'll say temperature should be greater than delta H upon delta S. Temperature should be greater than delta H upon delta S, right? Now, is delta H for the reaction given? Absolutely, it's given. But delta S for the reaction is not given. Delta S for the reaction is not given. So let's calculate delta S for the reaction. Entropy of product. So it's 1 multiplied by entropy of XY3 minus entropy of reactant. So it's half of entropy of X2 plus 3 by 2 times entropy of Y2. So delta S for the reaction will be equal. What is the entropy of XY3? Entropy of XY3 is nothing, that's 50 minus. This is half of. Entropy of X2 is 60 plus 3 by 2 times. Entropy of Y2, that is 40. Correct? So entropy change of the reaction has to be equal to 50 minus, this will be 30 plus, this will be 60. So 90 minus 50 comes out to be minus 40. So minus 40 joules per Kelvin. This is the entropy change of the reaction. And we know temperature has to be greater than delta H upon delta S. Delta H is minus 30 kilojoules. So convert it into joules. So minus 30,000 joules. Minus 30,000 joules. Right? Divided by. Minus 30,000 joules divided by delta S. Delta S is minus 40 joules per Kelvin. So minus minus cancel. So temperature has to be greater than 750 Kelvin. Temperature has to be greater than 750 Kelvin. Then only we can say this particular process will be spontaneous. That's something which you were supposed to calculate. Tell me once in the chat if it's clear. Say yes or no in the chats quickly. Simple again. Yeah? Quickly, people. Is this clear? These sort of questions are frequently asked, right? At what temperature the process will be spontaneous, non-spontaneous, etc. So temperature has to be greater than 750 Kelvin, then only I can say the process is going to be spontaneous. Okay? Now, guys, there is one more thing which I would want to discuss with you first of all. What is that? That is, what is that? That is Gibbs free energy, or let me write it like this: calculation of delta G for the reaction from Gibbs free energy of formations of reactants and products. This is one more small topic which I would want to discuss with you. It's simple, guys. It's very simple. For example, you've got a reaction like this: N1A plus N2B. It gives N3C plus N4D. Now, for example, I'm asking you to calculate Gibbs free energy change for the reaction. You will say it is going to be equal to Gibbs free energy of formation of products minus Gibbs free energy of formation of reactant. How exactly you are going to write it? Gibbs free energy of formation of products. So these are your products. So start with N3. N3 multiplied by free energy of formation of C plus N4 multiplied by free energy of formation of D. So this is your free energy of formation of products minus free energy of formation of reactants. Reactant is your A and B. So first of all, start with Na. Free energy of formation of A plus N2 multiplied by free energy of formation of B. Right? This is how you calculate the free energy change of the reaction. Gibbs free energy change of the reaction. Now, you can write it under standard conditions as well. Standard Gibbs free energy of the reaction is equal to standard free energy formation of C, standard free energy of formation of all these reactants and products, right? And do remember one simple thing. Standard Gibbs free energy of formation of an element which will be present in its standard state, that will be taken as 0. Standard free energy of formation of an element which will be present in its standard state, that will be taken as 0. What is standard state of an element? That state in which element exists in nature. Oxygen in nature exists in the form of O2 gas. Hydrogen exists in the form of H2 gas, right? Perfect. Iron exists in the form of Fe solid. Perfect. So these are the standard states of these elements. So if I write something like this, delta G naught formation of O2 gas. Is O2 gas the standard state of oxygen? Absolutely. So this value has to be 0, right? Similarly, for H2 gas, 0. For Fe solid, 0. And similarly, if you will be having any element which will be existing in the form of allotropes. So this is allotrop 1, this is allotrop 2. Allotrop 1, allotrop 2. That particular allotrop which will be thermodynamically more stable. For example, 2 is more stable than first. That particular allotrop which will be thermodynamically more stable, which will be considered as the standard state of the element. For example, if I talk about carbon, carbon has got two main allotrops. One is diamond and one is graphite. And thermodynamically, graphite is considered to be more stable. If graphite is considered to be more stable, that means if I write carbon like this, carbon graphite, this is going to be the standard state of carbon. And delta G naught for the formation of carbon graphite will be directly taken as 0. I hope this thing you will be remembering from now onwards. Is this clear? Is it clear, guys? Is it clear? See what kind of basic question this is. You are given with a reaction. We need to calculate standard Gibbs free energy change for the reaction, which will be equal to standard Gibbs free energy of formation of products minus reactants. So I'll start with 1 multiplied by delta G naught F of carbon dioxide plus 1 multiplied by delta G naught F of H2. This is the standard Gibbs free energy of products minus standard Gibbs free energy of reactants. So 1 multiplied by delta G naught F of carbon monoxide plus 1 multiplied by delta G naught F of water. Now see if all the parameters are given or not. Delta G naught F of carbon dioxide is given to us minus 400. H2, hydrogen is in standard state. It's going to be 0. This value is given. This value is given. Put all the values and get the answer. That's all. Put all the values and get the answer. That's all. Yeah. Is it clear? You should be able to solve this sort of a question as well. It's very simple and basic. It's very simple and basic. Now, guys, let's talk about the physical significance first of all. What is the physical significance of Gibbs free energy? This is important. Physical significance of Gibbs free energy. Before talking about the physical significance of Gibbs free energy, let me tell you one more thing. When we talk about work is actually of two types. Work is actually of two types. One is called as PV work, pressure volume work. One more is called as non-PV work. Non-PV work. Non-PV work is also called as useful work. And the example of the useful work is, for example, electrical work. It is, for example, electrical work. Now, what all these things means, first of all. For example, this is the container which we have. And in this container, I have kept an ideal gas. This is the ideal gas in the container, right? Now, for example, the piston is moving from A to B against external pressure. The piston is moving from A to B. So this is expansion. You know, whenever there is expansion or compression, in presence of external pressure, what happens? Energy is exchanged between system and surroundings in the form of work. And that work is something which you call as PV work, pressure volume work. So if the piston is moving from A to B, for example, then this is the case of expansion. We always say work is done by the system. But which work? This is the case of PV work, basically. This is the pressure volume work which is happening here. Similarly, during compression, work is done on the gas. Which work is done on the gas? It is the pressure volume work which is done on the gas. So whatever work we were discussing till now, that is basically PV work. That work which happens when the piston moves, right? Except free expansion. Leave free expansion aside. Okay, whenever you see piston moving either outwards or inwards, right? Exchange of energy between system and surroundings takes place in the form of what? Work. And which work that is? That is the pressure volume work which I'm talking about. So this is the pressure volume work which is happening here. So over here, energy between system and surroundings is exchanged in the form of pressure volume work. Now, what is this non-PV work? What is this useful work? Let's try to understand what this useful work is all about. I'm sure every one of you would have come across the Daniel cell. Do you remember? Daniel cell. Your galvanic cell. Right? This is your anode. This is your cathode. And they are connected. They are connected from the top. And internally they are connected with the help of salt bridge. Right? You must have studied about this. Perfect. What is the function of the Daniel cell basically? What is the function of this galvanic cell? What this Daniel cell does? It generates electricity. It generates current. It produces current. Daniel cell, what does it do? It produces current. How it produces current basically? Basically, in case of Daniel cell, there will be movement of electrons from anode to cathode. There will be movement of electrons. There will be directional movement of electrons from anode to cathode, due to which current is generated. In case of Daniel cell, right? In case of Daniel cell, what happens? Electrons move from anode to cathode. So there will be directional movement of electrons from anode to cathode. Absolutely. Yeah. Now, my dear students, first of all, if I ask you in this part of the cell, which work is going on? Can I say electrical work is going on? It is the electrical work which is going on here, right? Electron is being pushed from anode to cathode. Electrical work is going on basically. And electrical work, that is basically the example of what? That is the example of non-PV work. So I would say non-PV work is going on here, right? Non-PV work is going on here. Perfect. Non-PV work is going on here. Similarly, for example, this is an electrolytic cell. For example, I have taken water in the container. This H2O liquid in the container. For example, I'm introducing two rods here in this container. Now, here you have got a battery. What this battery does? It is going to supply current in the water. Battery will supply current in the water. right? So in this part of the cell, what is happening? Electrical work is happening. What is electrical work? Electrical work is the example of non-PV work. It is the example of non-PV work. And when current will go into the water, electrolysis of water will happen. Water will get converted into H2 gas. And you will be getting what? You'll be getting O2 gas as well. During the electrolysis of water, what will happen? Gases will produce. H2 gas will produce, O2 gas will produce. On the reactant side, you have got liquid. On the product side, you have got gas. So liquid is getting converted into gas. Expansion is happening. Which expansion this is? So imagine as if there was a piston here. Imagine as if there is a piston here. Just imagine there is a piston here. Since gases are getting produced, the piston will go up. If the piston will go up, what will happen? Expansion will happen. Due to expansion, what happens? Energy is exchanged between system and surroundings in the form of which work? In the form of PV work. I would say over here non-PV work is happening because electrons are being pushed, right? Non-PV work is happening, electrical work is happening, and right here, due to the expansion, I would say PV work is happening. Did you get the difference between what is PV work and what is non-PV work? I hope you got it. What is PV work and what is non-PV work? What is PV work and what is non-PV work? Try to understand one more thing. For example, I'm again taking the Daniel cell into consideration. This is anode and over here this is your cathode. You are connecting them externally. You're connecting them externally. This is your anode and this is your cathode. And internally also you're connecting them. So this is your Daniel cell, for example. Okay. First of all, what happens in the Daniel cell? Electrons are moved from anode to cathode. Right? So in this part, what is happening? What is happening? Electrons are being pushed basically. Electrical work is happening over here. Electrical work is the example of non-PV work. So non-PV work is happening. Non-PV work is happening. Non-PV work is also called as useful work. Through which, so basically electrons are being pushed from anode to cathode. So non-PV work is happening. That's what you call as useful work, right? Now, my dear students, do remember, as I told you in the beginning also, in the system, you'll find two types of energies, available and unavailable. In the system, what you'll find? You'll find two types of energies, available and unavailable. Available and unavailable energy. Available energy, it is that part of the energy which is converted into what? Which is converted into useful work. What kind of useful work is happening here? Basically, electron is being taken from anode to cathode. Electron is taken from anode to cathode. So work is happening, electrical work is happening. In order to take the electron from anode to cathode, system will be using some of its energy. Now, which energy system will be using for this electrical work? It is the available energy which the system will be using to perform this electrical work, to perform this non-PV work. Yeah? Imagine that in the beginning, the system had 80 joules of available energy. After some time, you saw only 60 joules of available energy is present in the system. Initially, for example, 80 joules of available energy was with the system. Now, after some time, only 60 joules of available energy is left with the system. So, has the available energy of the system decreased or increased? It has decreased. By how much amount? Has the available energy of the system increased or decreased? It has decreased by 20 joules. What does that mean? Available energy of the system has decreased. That means some part of available energy has been utilized to perform non-PV work, to send electrons from anode to cathode, right? So can I say decrease in the free energy, decrease in the Gibbs free energy, decrease in the available energy is equal to useful work? Can I say 20 joules of useful work has been done in order to take the electron from anode to cathode? Yeah? So I can simply say one thing, decrease in the Gibbs free energy. Decrease in the Gibbs free energy of the system. Decrease in the Gibbs free energy of the system is equal to useful work, is equal to non-PV work. Right? Perfect. So what is Gibbs free energy now? It is that part of the energy of the system which is converted into what? Which is converted into useful work. Let's try to understand all this mathematically, because without mathematics, this all is useless, right? And then you can understand a bit more in detail. First of all, I'm going to mark an equation. I'm going to write an equation. What is an equation? Equation is, just a second. You know, G is equal to H minus Ts. G is equal to H minus Ts. Try to understand what I'm going to say. G is equal to H minus Ts. If I multiply throughout by D, it becomes dG is equal to dH minus D of Ts. So I can write it like this. dG is equal to dH minus TdS minus SdT. Okay. If I write this equation at constant temperature, my dear students, dt is 0. If dt is 0, I would say dg is equal to dH minus TdS. Perfect. Now, since we know what is H, H is equal to U plus PV, right? If I write dH, dH will be equal to du plus d of PV. So you can write it like this. dH is equal to du of PdV plus VdP. If I write the same equation at constant pressure, I must say dH is equal to du plus PdV, because at constant pressure, dP value is 0, right? So dH is equal to du plus PdV. It's valid at constant pressure. So I can say dG is equal to, instead of dH, I can write du plus PdV. And already there was minus TdS. Now try to understand. This equation we wrote at constant temperature. And this equation we wrote at constant pressure, right? And we are putting the value of dH over here. That means this particular equation. It is valid at constant pressure and temperature. Initially, we wrote this particular equation at constant temperature, and this particular equation we wrote at constant pressure. Putting it in this equation, that means the final equation which we are getting, that's valid at constant pressure and temperature. Point number 1. Point number 2. You know, as per first law, du is equal to dq plus dw. I'll write dw net. du is equal to dq plus dw, right? Okay, du is equal to, okay, I'll tell Ambika about that, no issues. du is equal to dq plus dw. For example, we have a system. For example, the system which we have. Let's say that is capable of doing, let's say we have got the system which is capable of doing PV as well as non-PV work. Let's say that we have got a system which is capable of doing PV as well as non-PV work. So what is going to happen? If we have got a system which is capable of doing PV as well as non-PV work, something interesting is going to happen. Try to understand. We'll write dG is equal to, what is du? du is dq plus dw net. Then what do we have? du is equal to dq plus dw. Then you have got PdV as well. And then you have got TdS as well. I told you the system, for example, is capable of performing PV work as well as non-PV work. So instead of dw net, I can write dw PV plus dw non-PV, right? And already there was PdV and TdS. So I can say dG is equal to dq. dw of PV. PV work is equal to minus PdV plus dw of non-PV plus PdV minus TdS. So see what all things will get cancelled out. Or one more thing. You know, your ds is equal to dq reversible upon temperature. So I can say dq is equal to TdS. Perfect. So instead of dq, you can write TdS minus PdV plus dw non-PV plus PdV minus TdS. See what all parameters will get cancelled out. So this term got cancelled, right? PdV got cancelled. So finally, I'm getting something like this. dG is equal to dw non-PV. dG is equal to dw non-PV. If I integrate on both the sides, I'm getting delta G is equal to non-PV work. Delta G is equal to non-PV work. Is this something which I told you a few minutes back only? Is this something which I told you a few minutes back only? What is this? Delta G is equal to non-PV work. What is the significance of this particular equation? It means some part of Gibbs free energy is used for what? is converted into useful work, is converted into non-PV work. Yeah. It's simply this equation simply tells you that the part of the Gibbs free energy is utilized for useful work, is converted into useful work, right? Now from this equation, there are few things which you can analyze. I told you delta G is equal to W non-PV. Delta G is equal to W non-PV. Try to understand what all things I'm going to say from here. When I took the galvanic cell, if you remember, when I took the galvanic cell, the electron was moving from anode to cathode, right? So electrical work was happening basically. Yeah, electrical work was happening. That is useful work. That is non-PV work. Now non-PV work was happening. Now, my dear students, I told you, in order to take the electron from anode to cathode, system will be utilizing some of its energy. Which energy system will be utilizing basically? The system will be utilizing its available energy to send the electron from anode to cathode. So with time, the available energy of the system will decreasing because some part of it is utilized to send the electron from anode to cathode. So decrease of available energy is happening to send electron from anode to cathode. So non-PV work is done by the system at the cost of its available energy, right? So non-PV work is done by the system at the cost of its available energy. With time, available energy will decrease, due to which non-PV work will be done by the system. Let's try to understand it now. My dear students, for example, the value of W over here comes out to be negative. If the value of W is coming out to be negative, what does that mean? That means non-PV work or useful work is done by the system. Just relate it with the Daniell cell. Just try to relate it with the Daniell cell as if system is sending electrons from anode to cathode. Okay? Non-PV work is done by the system. At the same time, if W non-PV is negative, that means delta G is negative. That means delta G is negative. Delta G negative means free energy of the system is decreasing. So whenever you see free energy of the system decreasing with time, understand at that point of time, non-PV work will be done by the system because some part of the available energy, some part of Gibbs free energy will be converted into useful work. That is the reason why Gibbs free energy will be decreasing with time. I hope this is clear. Similarly, one more statement. If W non-PV is positive, what does that mean? That means non-PV work is done on the system. Non-PV work is done on the system, right? If W is positive, if W non-PV is positive, what does that mean? That means delta G is positive. If delta G is positive, that means Gibbs free energy of the system increase with time. So whenever you see the Gibbs free energy of the system increasing with time, that means at that time non-PV work is done on the system. Whatever non-PV work is done on the system, that entire non-PV work is stored in the system in the form of its Gibbs free energy. Yeah? Perfect. So do remember these two particular statements. I hope these are super clear to you, right? One last topic is there. First tell me, is this particular thing clear to you? What have I said till now? Is this particular thing clear to you? When non-PV work is done by the system, at that time Gibbs free energy of the system will be decreasing because some part of Gibbs free energy is converted into useful work. That's the reason why Gibbs free energy decreases. Okay? When? But when non-PV work is done on the system, whatever non-PV work is done on the system, that entire non-PV work is stored in the gas in the form of Gibbs free energy, due to which Gibbs free energy will increase with time. Non-PV work done on the system, Gibbs free energy increases for the system. Non-PV work is done by the system, Gibbs free energy decreases. Perfect. Do remember this particular result. This is important. Sometimes they won't ask you directly to calculate delta G. They'll ask you to calculate non-PV work. They'll ask you to calculate non-PV work. Non-PV work is nothing, that's delta G only. Then use the formula delta H minus T delta S, whatever. Right? Sometimes they can confuse you. Directly, either they'll directly ask you to calculate delta G, or they can ask you to calculate the non-PV work done by the system or on the system. That means indirectly they're asking you to calculate delta G only. I hope this is clear. All right, one last topic, guys. With that, we'll be ending the chapter. And this is important too. I'm writing variation of Gibbs free energy with pressure and temperature. Variation of Gibbs free energy with pressure and temperature. Let's get to know how Gibbs free energy changes on changing pressure, on changing temperature. Let's have a look. Yes, this is a detailed course. Now, guys, try to understand. First of all, I'm going to write one equation, which you are going to remember directly from now onwards. dg is equal to vdp minus sdt. This is the backbone of the thermodynamic, this particular equation. dg is equal to vdp minus sdt. This particular equation you are going to remember directly from now on, right? And let me tell you, this particular equation, it is valid for reversible processes. It is valid for reversible processes. Now, understand what exactly I'm going to say. Point number one. For an ideal gas, let's say you have got the ideal gas, which is kept at constant temperature. Let's say you have got the ideal gas whose temperature is kept fixed. We are not changing the temperature of the ideal gas. If temperature is constant, if temperature is fixed, that means dT value will be 0. Change in temperature will be 0. If dT is 0, that means dG will be equal to vdP. dG will be equal to vdP. This particular equation is valid for that ideal gas whose temperature is kept constant, right? Now, my dear students, the ideal gas whose temperature is kept constant, let's say you increase its pressure. If you increase its pressure, what will happen to the dP value? Change in pressure. Will it come out to be positive or negative? If you increase the pressure of this ideal gas, dP, change in pressure, will be positive. If dP is positive, this whole term is positive. And if this whole term is positive, that means dG is positive. And when is dG positive? Change in Gibbs free energy? When G increases. dG is positive only when G is increasing. Right? So what can we conclude from here? On increasing the pressure of the ideal gas, Gibbs free energy of the ideal gas increases. So Gibbs free energy is directly proportional to pressure of the ideal gas, provided temperature of the gas is kept constant. Yeah, provided the temperature of the gas is kept constant. If you increase the pressure of the gas, Gibbs free energy of the gas will automatically increase, provided the temperature is constant. Now, on changing the pressure, Gibbs free energy increases. How much Gibbs free energy increases on changing the pressure? That is important also. For example, I'm changing the pressure of the gas from P1 to P2. Let's say I'm changing the pressure of this gas from P1 to P2, right? Since we know dG is equal to vdP. Since we know dG is equal to what? Since we know dG is equal to vdP for the ideal gas which is kept at constant temperature, right? Now, what are we doing? We are changing the pressure of the ideal gas from P1 to P2. We need to see what is the total Gibbs free energy change. In order to calculate total Gibbs free energy change, we'll be integrating, right? We'll be integrating from P1 to P2. We'll be integrating with respect to pressure, since we are changing pressure from P1 to P2, right? So guys, integral of dG is delta G is equal to integral from P1 to P2. V is equal to nRT divided by P, and this is dP. So delta G has to be equal to nRT comes out. Integral of dP is ln of P, so upper limit, lower limit, so ln of P2 divided by P1, or you can write it like this. Delta G is equal to minus 2.303 nRT. It's going to be log of P2 divided by P1, right? What equation this is? And when it's used? This equation is used to calculate the Gibbs free energy change of an ideal gas, which is kept at constant temperature, whose pressure we are changing from P1 to P2. Since we got to know on changing the pressure of the ideal gas, Gibbs free energy changes. Now, how do we calculate that change in the Gibbs free energy on changing the pressure at constant temperature? This is the result. If you change the ideal gas pressure from P1 to P2, keeping temperature constant, how do we calculate delta G? Change in the Gibbs free energy of the ideal gas. It has to be equal to 2.303 minus. Wait, is it minus? It's not minus. Why am I writing minus here? It was delta G is equal to nRT ln P1 by P. This is plus, this is not minus. Okay? Perfect. Muntazir, there is nothing like 11th, 12th, right? It is all NEET and JE. Don't get confused, right? Whatever chapters are there in class 11, they're asked in NEET. So it's better if you study NEET. Don't be confused. Don't confuse yourself that you are in class 11th right now. You'll do the NEET coaching afterwards. You have to do the NEET coaching right now. I hope this particular statement is clear to you, right? Now, guys, there is one more thing. There is one more thing. The equation which I gave you in the beginning, that is dg is equal to vdp minus sdt. vdp minus sdt, which is valid for the reversal process, right? Now, imagine that we have got the ideal gas. I'm writing for ideal gas. For ideal gas at constant pressure. Let's say you have got the ideal gas which is kept at constant pressure. Let's assume that we have got the ideal gas which is kept at constant pressure. If the ideal gas is kept at constant pressure, so change in pressure dP has to be 0. If dP is 0, then dG will be equal to minus times S dt. dG will be equal to minus times S dt, right? So basically, what exactly I'm going to do? I'm taking an ideal gas whose pressure I'm maintaining. I'm keeping the pressure constant. So I got to know dG for the ideal gas whose pressure is constant is equal to minus times S dt. Now you tell me one thing. If you increase the temperature of the same ideal gas, change in temperature dt will come out to be positive. If dt is coming out to be positive, positive negative makes it negative. So dg has to be negative. Change in Gibbs free energy is negative. That means Gibbs free energy of the system decreases. What does that mean? That means if you increase the temperature of the ideal gas, the Gibbs free energy of the gas will decrease. So Gibbs free energy is inversely proportional to temperature of the gas. It is inversely proportional to temperature of the gas provided the pressure of the gas is kept constant. Provided the pressure of the gas is kept constant, right? Perfect. Now, you got to know your dg is equal to minus times S dt. Perfect, right? So, what exactly we are going to do? For example, you have got the ideal gas in the container. This is the ideal gas in the container, right? Let's say, okay, do remember it like this only. dg is equal to minus S dt. But do remember this is valid for the ideal gas whose temperature you are changing, keeping pressure constant. So till now I was talking about gases, basically ideal gases. Now, for example, if you have solid or liquid, for solids or liquids, if your system is not the ideal gas, if your system is, for example, solid or liquid, what will happen? For solids and liquids, when you change the pressure of solid and liquid, when you increase or decrease the pressure of solid and liquid, I'm talking about this particular case. This was the case for the ideal gas which is kept at constant temperature, right? When you increase the pressure of the ideal gas, Gibbs free energy increases, right? But imagine that your system is not the ideal gas. Imagine the system is your solid or liquid. So I'm writing for solids or liquids. For solids or liquids kept at constant temperature. If you change the pressure, first of all, for solids, liquids kept at constant temperature, we know dg is equal to vdp minus sdt. If temperature is constant, this term is 0. So dg has to be equal to vdp, correct? Right? Now, guys, imagine that this is a solid or a liquid. Which is kept at constant temperature. Now you are changing its pressure. You are changing the pressure of solid or a liquid. Due to change in pressure, volume of the solid or liquid will not change significantly. There will be negligible change in the volume of solid or liquid. If you have a solid or a liquid in a container, if you change its pressure, there will be negligible change in its volume, right? There will be negligible change in its volume. Imagine this is a solid. Let's assume that you are changing the pressure of the solid from P1 to P2. I need to calculate the total change in Gibbs free energy due to change in pressure of the solid whose pressure you are changing from P1 to P2. In order to get the total Gibbs free energy change, you'll be integrating under the limits P1 to P2. So integral of dg is delta G. Since on changing the pressure, volume of solid or liquid, it does not significantly change. So volume is kept constant, V coming out. Integral of dP is P, upper limit, lower limit. So it has to be P2 minus P1. So delta G is equal to V delta P. But this particular result, it's valid only for solids or liquids, which are kept at constant temperature. So if you'll be having a solid or a liquid, which is kept at a constant temperature, and you're changing its pressure, on changing the pressure, you have to check what will be its change in Gibbs free energy. This is the result which you'll be using to calculate the change in the Gibbs free energy of a solid or a liquid whose pressure you are changing from P1 to P2 at a particular temperature, right? I hope all these results, whichever I told you, I hope you guys are going to remember them. Okay? All right, what do you think about this question? Will you be able to solve this? What is the free energy change when 1 mole of H2O liquid? So you have got 1 mole of H2O liquid at 100 degrees centigrade and 1 atm pressure is converted into steam, is converted into H2O gas at 100 degrees centigrade and 1 atm. So during the process, we have to calculate delta G value. Can you let me know what is the value of delta G during this process? This is your homework question which I'm giving you. You are converting H2O liquid into H2O gas. Temperature is same, pressure is same. Calculate delta G during the process. Calculate delta G during the process. Or let me tell this question here only. See, are you changing the pressure of the system? No. Are you changing the temperature of the system? No. Neither you are changing pressure nor you are changing temperature. So delta G value has to be 0, right? Or you know, at 1 atm 100 degrees centigrade, 1 atm 100 degrees centigrade, can I say liquid and gas, they'll be in equilibrium, right? They'll be in equilibrium. At 100 degrees centigrade, your liquid and vapors, they're at equilibrium. If pressure and temperature on both the sides is equal, temperature is 100, pressure is 1 atm, right? So it is basically the boiling point of water. At boiling point, your liquid and vapors, they are at equilibrium. And at equilibrium, you already know delta G is 0. So like this also you can solve this. Okay, like this also you can solve it. Perfect. One question, which is your homework question. This is something which you guys are going to solve. Again, you are vaporizing 1 mole of liquid water, keeping temperature same, but you are changing pressure from 1 atm to 2 atm. You have to calculate the value of delta G during the process. You have to calculate the value of delta G during the process, right? This is your homework question. You guys will be letting me know the answer of this particular question in the comment section, right? And let me remind you, day after tomorrow, Saturday at 5 p.m., we will be doing your chemical equilibrium in one shot. Chemical equilibrium in one shot will happen on Saturday, 5 p.m., right? So be there on time. Perfect. Is everything clear till here? All clear? All right, guys. So with this, I'll be taking a leave. And at the same time, if you want the handwritten PDF of this particular session, this is the Telegram group, t.me/WASSIMSIRCHEM. This is the Telegram channel, right, on which I'll keep on sharing the session PDFs and things, right? I hope whatever I taught you in the today's session, I hope every single thing is clear, right? With this, our thermodynamics part is clear. Now we are left with thermochemistry. That is a separate chapter which we shall be doing. Okay, that's a separate chapter which we shall be doing. In the Conquer batch, the syllabus will complete maybe in October, right? Because till now I'm done with a lot of chapters, right? Mole is done, states of matter is done, solids is done, chemical bonding is done, now thermodynamics is done, right? And redox is also done. So I'm done with 6 chapters. HSP sir is also done with 2-3 chapters, right? So we'll finish the syllabus before time only. You need not to worry about that. Perfect. Hello guys, I'll take a leave. We'll catch up on Saturday. Bye-bye.